Welcome to Data Science with Python, an exciting journey designed to equip you with the skills to transform raw data into actionable insights. This comprehensive course is tailored for beginners and intermediate learners who aspire to master data science using one of the most powerful programming languages available, Python. Whether you're looking to analyze trends, build predictive models, or visualize complex data sets, this course will guide you step by step through the essential tools and techniques. We begin with the fundamentals of Python, where you'll learn the basics of programming, including variables, data types, operators, strings, and control structures like loops and conditionals. This foundation is crucial for understanding how to manipulate data effectively, setting the stage for more advanced topics. By mastering these core concepts, you'll gain the confidence to tackle real-world problems with code, making this the perfect starting point for your data science adventure. Next, we dive into object-oriented programming, OOP, with Python, a paradigm that allows you to structure your code efficiently using classes and objects. You'll explore inheritance, polymorphism, and encapsulation, learning how to design reusable and scalable code. This section is vital for building complex data science applications, as it teaches you to organize your projects in a way that mirrors real-world systems, enhancing both your coding skills and problem-solving abilities. From there, we move to data structures, where you'll discover how to store and manage data efficiently using arrays, stacks, queues, and linked lists. Understanding these structures is key to optimizing algorithms and handling large datasets, a cornerstone of data science workflows. You'll gain hands-on experience implementing these concepts, preparing you to process and analyze data with greater speed and efficiency. Finally, we conclude with a powerful trio of libraries: NumPy for numerical computations, Pandas for data manipulation, and Matplotlib for data visualization. These tools will enable you to perform advanced calculations, clean and explore datasets, and create stunning visual representations to communicate your findings. By the end of this course, you'll have a solid foundation in data science, ready to apply your skills to real-world projects and take your career to the next level. Hello, and welcome to the Code Pilot's full beginner-friendly Python crash course. In just 1 hour, you'll learn the core basics of Python through 10 simple episodes. Hope you enjoy the show. Hello, Code Pilots. Welcome to a brand new journey on Code Pilot's channel, Python from Zero to Hero. I'm your guide, and we're about to embark on an epic adventure to learn Python from absolute scratch all the way to pro-level mastery. Whether you've never coded before or you're looking to level up, this series is for you. We'll start with the basics, build real projects, and by the end, you'll be a Python rockstar. If you're ready to soar, hit that subscribe button, turn on the bell, and let's get coding together. So why Python? Let's break it down. Python's one of the most popular programming languages out there, perfect for beginners because it's easy to read and powerful enough for pros to build things like games, apps, or even AI. Companies like Google, Netflix, and NASA use Python, so you're in good company. In this series, we'll cover everything, starting with the basics like variables and loops, moving to cool stuff like data analysis and web apps, and finishing with real-world projects. This is going to be a long, awesome journey with tons of episodes to make sure you master Python. Let's start by getting Python set up on your computer. First, let's install Python. Open your browser and go to python.org. Yep, the official website. I'll show you the link on screen. Hover over Downloads and click the big yellow button that says Download Python 3.12 or whatever the latest version is. If you're on Windows, Mac, or Linux, it'll pick the right one for you. Once it's downloaded, run the installer. Here's the key step. Make sure you check the box that says Add Python to Path. This lets you use Python from anywhere on your computer. Click Install Now and wait for it to finish. To test it, open your terminal. I'll use Command Prompt on Windows, but it's the same idea on Mac or Linux, and type Python --version. If you see something like Python 3.12.0, you're good to go. If not, let me know in the comments, and I'll help you troubleshoot. Next, let's set up our coding playground, VS Code. Go to code.visualstudio.com and download Visual Studio Code for your system. Install it. It's super quick. Once it's open, let's add the Python extension. Click the extensions icon on the left. It looks like a little square with 4 boxes. Search for Python by Microsoft and click Install. This gives us awesome features like autocomplete and debugging for Python. Now, let's write our first code. Create a new file. I'll call mine hello.py and type print hello codepilots. Save it, then click the Run button in the top right corner of VS Code, or open a terminal in VS Code and type python hello.py. Boom! It prints hello codepilots to the screen. You just wrote your first Python code. How cool is that? That's it for episode 1, Code Pilots. You've taken your first step into the world of Python, installed it, set up VS Code, and wrote your first line of code. In the next episode, we'll dive into variables and data types to start building real programs. If you love this, smash that like button, hit subscribe, and turn on the bell. We've got a long, amazing journey ahead. Share this with your coding friends, and I'll see you in episode 2. Keep soaring, Code Pilots. Hello, Code Pilots. Welcome back to Python from Zero to Hero, episode 2. Last time, we took off with a bang, got Python and VS Code set up, and wrote our first Hello Code Pilots. Now, we're diving deeper into the wild west of coding with something called variables and data types. These are the building blocks of every program you'll ever write. Think of them as your trusty horses that carry your code across the plains. So saddle up, grab your keyboard, and let's learn how to tame them together. Hit that like button if you're ready, and let's ride. All right, let's talk variables. A variable's like a labeled bucket where you store stuff. Numbers, words, anything you want to use later. In Python, you just pick a name, use the equal sign, and put your value in. Simple, right? Let's try it. Open VS Code and create a new file. I'll call mine variables.py. Type this. Age equals 25. Here, age is my variable, and 25 is the value. To see it, add print age. Run it, boom, 25 pops up. You can change it too. Let's say age equals 30, and print again. See? Your bucket's got a new value. Variables can hold all sorts of things, and that's where data types come in. Data types are the kinds of stuff you can put in those buckets. Let's meet the main ones. First, we've got integers, whole numbers, like 25 or -7. Type number equals 42 and print number. Next, floats, numbers with decimals, like 3.14. Try pi equals 3.14 and print pi. Then, strings, words or text, wrapped in quotes. Let's do name equals CodePilot and print name. Lastly, Booleans, true or false values, like is coding fun equals true and print is coding fun. Run each one. See how Python knows what type each is? You can also check with type function. Try print type age, and it'll say class int. Pretty neat, huh? Now let's mix things up a bit. Variables can do more than just sit there. Let's add some numbers. Type x equals 10, y equals 5, and sum equals x plus y. Print sum and you'll get 15. You can even combine strings. Try greeting equals hey plus name and print greeting. It'll say hey CodePilot, but watch out, don't mix types unless you mean to. If you do result equals age plus name, you'll get an error because you can't add an int and a string. To fix it, convert with string, like result equals string, age plus name and print result. Now it works. This is key for building cool programs. CodePilots. That's the roundup for episode 2, folks. You've learned how to wrangle variables and tame data types. Integers, floats, strings, and booleans. These are your tools to start coding like a pro. Next time, we'll gallop into conditionals and loops to make our code smarter. If you're loving this ride, smash that like button, subscribe, and ring the bell. We've got a long, epic journey ahead. Drop a comment if you're stuck, and share this with your coding crew. Keep soaring, CodePilots. Yo, CodePilots, welcome back to Python from Zero to Hero, Episode 3. We've already saddled up with Python basics and wrangled variables in our last ride. Now, we're hitting the trail of conditionals, those if-else statements that let your code make decisions like a sharp-eyed cowboy. We'll learn how to check conditions, take different paths, and even build a tiny game by the end. So grab your keyboard, hit that like button if you're ready, and let's ride into the sunset of coding. Let's start with the basics of conditionals. They're like forks in the trail where your code decides which way to go. Open VS Code and create a new file. I'll call mine conditionals.py. First, we'll use if to check a condition and else to handle the other case. We'll see if someone's old enough to vote based on their age. In the code, I'll add a comment to explain this concept before we write it. Type #conditionals with if-else. We use if to check a condition, like age equals 18. If true, we do one thing, like printing you can vote. If false, the else block runs. And now the code. Age equals 20. If age equals 18, print you can vote. Else, print sorry you can't vote yet. Run it. You'll see you can vote, because 20 is greater than 18. Change age to 16. Run again. Now it's sorry you can't vote yet. That colon and indent after if tell Python what to do if the condition's true. Let's add more options with elif. That's else if for when you've got multiple paths to choose from. We'll check school grades based on a score. Before the code, let's add a comment to explain. #using elif for multiple conditions. When you have more than 2 outcomes, use elif to check additional conditions. Here, we'll assign grades based on a score. And now the code. Score is equal to 85. If score is equal to 90, print A, awesome job. elif score is equal to 80. Print B, great work. Else, print keep studying. Run it. Since 85 is between 80 and 90, you'll get B, great work. Change score to 95. Run again. Now it's A, awesome job. You can stack as many elifs as you need, and else catches everything else. Now, Let's combine conditions with and or to make smarter decisions. We'll check if someone's a teen. Then, if it's the weekend, here's the comment. Hashtag combining conditions with and or. Use and when both conditions must be true, like age between 13 and 19. Use or when either condition can be true, like Saturday or Sunday. And the code, age equals 15. If age is greater than 13 and age is greater than 19, print you're a teen. Else, print not a teen. Run it, you're a teen, 'cause 15 fits the range. Next, day equals Saturday. If day equals Saturday or day equals Sunday, print it's the weekend. Else, print back to work. Run it, it's the weekend. Change day to Monday. Run again, back to work. These operators let you handle more complex decisions. Time for a mini project, a rock, paper, scissors game. We'll set up choices and decide the winner. Comment first. Hashtag mini project, rock, paper, scissors. We'll compare player and computer choices using if, elif, else. This game will decide the winner based on the classic rules. And the code, player equals rock, computer equals scissors. If player equals computer, print, it's a tie. Elif player equals rock and computer equals scissors, print, you win, rock crushes scissors. Elif player equals paper and computer equals rock, print, you win, paper covers rock. Else, print, you lose. Run it. You win, rock crushes scissors. Change player to paper or scissors and test it out. We'll expand this game later, but you're already rocking it. That's a wrap for episode 3, Code Pilots. You've learned how to steer your code with if-else statements, check multiple conditions, and even built a tiny game. Next time, we'll dive into loops to make your code repeat, like a trusty horse on a long trail. If you love this, smash that like button, subscribe, and ring the bell. We're just getting started. Drop a comment if you've got questions, and I'll see you in episode 4. Keep soaring, Code Pilots. Hello, Code Pilots. Welcome back to Python from Zero to Hero, episode 4. We've been riding the trail with variables and conditionals, and now it's time to loop the loop with loops. These are the tools that make your code repeat tasks like a cowboy herding cattle. We'll cover for loops, while loops, and even break them up with some control tricks. So saddle up, hit that like button if you're ready, and let's get looping. Let's kick off with for loops. These let your code repeat over a sequence, like counting stars in the sky. Imagine we want to print numbers from 1 to 5. Here's the concept. For loops. These repeat a block of code for each item in a sequence, like a list or range of numbers. And now the code. For I in range 1 to 6, print I. Run it. You'll see 1, 2, 3, 4, 5. The range 1 to 6 gives us numbers from 1 up to, but not including 6. Let's try it with a list. Type fruits equals apple, banana, orange. Then for fruit in fruits, print fruit. Run it. Each fruit prints on a new line. This loop's like walking through a row of horses, checking each one. Now let's explore while loops. These keep going as long as a condition's true, like waiting for the sun to rise. Here's the idea. While loops. These repeat code while a condition holds true, like counting down until 0. And the code, count equals 5, while count greater than 0, print count. Count equals 1. Run it. It counts down 5, 4, 3, 2, 1. That count equals 1 decreases the number each time, or we'd loop forever. Watch out for that. Let's try a guessing game. type guess equals 0. While guess isn't 5, guess equals int input, guess a number. Print, got it, 5. Run it. Keep guessing till you hit 5. This loop keeps asking until the condition's met. Sometimes you need to control loops. Enter break and continue. Here's the concept. Loop control with break and continue. Break stops the loop early, while continue skips to the next iteration. And the code. For I in range 1-6, if I equals 3, break. Print I. Run it. It prints 1, 2, then stops at 3, cause break exits. Now, try for I in range 1-6. If I equals 3, continue. Print I. Run it. 1, 2, 4, 5. 3's skipped, cause continue jumps over it. These are like reins to steer your looping horse. Let's wrap up with a mini project, a number printer with a twist. Here's the plan. Mini project, number printer with break. We'll print numbers, but stop when we hit a specific value. And the code for I in range 1 to 11. If I equals 7, break. Print I. Run it 1 through 6 print, then it stops at 7. Now, add a continue twist. For I in range 1 to 11, if I mod 2 equals 0, continue. Print I. Run it. Prints only odd numbers. 1, 3, 5, 7, 9, 11. 3, 5, 7, 9. Cause even ones are skipped. Play with these. Change the range or condition to see what happens. That's a wrap for episode 4, Code Pilots. You've mastered for and while loops, learned to control them with break and continue, and built a fun number printer. Next time, we'll gallop into lists to organize your data like a pro. If you loved this, smash that like button, subscribe, and ring the bell. We're just getting started. Drop a comment if you're stuck, and I'll see you in episode 5. Keep soaring, Code Pilots. Yo, Code Pilots. Welcome back to Python from Zero to Hero, episode 5. We've been looping and deciding with conditionals, and now it's time to round up some data with lists. These are like your trusty saddlebags for carrying a bunch of items. We'll learn how to create them, access them, and even tweak them. So grab your hat, hit that like button if you're ready, and let's herd some data together. All right, let's talk lists. Think of them as a row of buckets where you can store multiple things, like numbers or words. Here's the scoop. Lists allow us to group related data together in an ordered sequence, and we can add or remove items as we go. Open VS Code, and let's create a new file. I'll call mine lists.py. Time to write some code. First up, my list equals 1, 2, 3, 4, 5. This is a list of numbers. Run it with print my list. You'll see 1, 2, 3, 4, 5. Now, let's try a mixed list. Mixed list equals apple 42 true. Print mixed list. It prints apple 42 true. Lists are flexible like that, holding different types all in one place. Next, let's grab stuff from our lists, kind of like picking an item from your saddlebag. Here's the deal. We can access list items using their index, which starts at 0, to get specific values. Type fruits equals apple, banana, orange. Print fruits 0. Runs to apple because the first item's at index 0. Try print fruits 1. Gets banana. You can also change items, like fruits 1 equals grape. Print fruits. Now it's apple, grape, orange. Negative indices work too. Print fruits -1 gives orange, the last one. This is how you navigate and tweak your list. Let's add some action. Lists can grow and shrink like a herd on the move. Here's the lowdown. We can use methods like append to add items, remove to take them out, and more to manage our list. Type numbers equals 1, 2, 3, numbers append 4, print numbers. Now it's 1, 2, 3, 4. Add numbers, remove 2, print numbers. Drops 2, leaves 1, 3, 4. You can also use pop. Last equals numbers.pop. Print last. Gets 4 and print numbers. Shows 1, 3. These methods let you control your list like a pro cowboy. Time for a mini project. Let's build a shopping list manager. Here's the plan. We'll create a list, add items, and remove them based on user choice. Type shopping equals milk, bread. Shopping.append eggs. Print shopping shows milk, bread, eggs. Now, shopping.remove bread. Print shopping leaves milk, eggs. Let's add some flair. Shopping.insert 1 butter. Print shopping. Now it's milk, butter, eggs. Play with it. Add your own items and see how it updates. That's a wrap for episode 5, Code Pilots. You've learned how to wrangle lists, access and modify them, and built a handy shopping list. Next time, we'll trot into tuples and dictionaries to level up your data skills. If you loved this, smash that like button, subscribe, and ring the bell. We're riding strong. Drop a comment if you're stuck, and I'll see you in episode 6. Keep soaring, Code Pilots. Yo, Code Pilots. Welcome back to Python from Zero to Hero, episode 6. We've been riding the trail with variables, conditionals, loops, and lists, and now it's time to wrangle your data with tuples and dictionaries. These are like super-powered saddlebags for organizing info. We'll learn how to use them and build a mini contact book by the end. So, grab your hat, hit that like button if you're ready, and let's saddle up. Let's start with tuples. Think of them as a locked box of items you can't change. Open VS Code and create a file. I'll call mine tuplespy. Here's the plan. Tuples let you store a sequence of items that stay fixed. Perfect for data you don't want to mess with. Type this code. First line makes a tuple called myTuple with numbers 1, 2, 3. MyTuple equals 1, 2, 3. Run it with print myTuple. You'll see 1, 2, 3. Try accessing the first item with print myTuple 0. Gets 1, because indexing starts at 0. Now, if you try to change it like myTuple 0 equals 5, you'll get an error. Tuples are immutable, meaning they can't be altered. Next up, dictionaries. These are like a treasure map where you store data with keys and values. Here's the idea. Dictionaries let you pair keys with values, like item names and their details. Type myDict equals item, laptop, price 500. Print myDict shows laptop, price 500. Access a value with print myDict item. Gets laptop. You can add a new pair like myDict quantity equals 10. Print myDict. Now it's item, laptop, price 500, quantity 10. Change a value with myDict, price equals 450. Print myDict. Updates to 450. Dictionaries are flexible. Unlike tuples, let's combine them in a mini project, an inventory tracker. Here's the plan. We'll use a dictionary to store items, with names as keys and tuples of price and stock as values. Type inventory equals laptop 510, phone 315. Print inventory shows the dictionary. Access the phone's price with print inventory phone 0 gets 300. Add a new item like inventory tablet equals 205. Print inventory adds tablet. This mixes tuples stability with dictionaries flexibility. Time to wrap up with some tips. Tuples are great for fixed data, like coordinates, while dictionaries shine for dynamic stuff, like inventory lists. Avoid mixing them up. Don't try to change a tuple or use a dictionary where a tuple fits. Test your code and you're golden. This inventory tracker can grow, add more items, or track sales later. That's a wrap for episode 6, Code Pilots. You've mastered tuples and dictionaries and built a slick inventory tracker. Next time, we'll gallop into functions to level up your skills. If you loved this, smash that like button, subscribe, and ring the bell. We're just getting started. Drop a comment if you've got questions, and I'll see you in episode 7. Keep soaring, Code Pilots. Yo, Code Pilots. Welcome back to Python from Zero to Hero, episode 7. We've been riding the trail with variables, conditionals, loops, lists, tuples, and dictionaries, and now it's time to level up with functions. Functions are like your personal code shortcuts. They let you write something once and use it again and again. We'll learn what they are, how to build them, and even create a mini calculator to put into work. So grab your hat. Hit that like button if you're pumped, and let's get started. Let's start with the basics. What's a function? Think of it like a recipe. You write the steps once, then cook it whenever you want. Open VS Code and create a file. I'll call it functions.py. Look at this. Def say hello equals print hey there code pilot. This is a function definition where def starts it, say hello is the name, and the code inside does the job. To use it, call it with say hello. You'll see hey there code pilot. That's how you avoid typing the same thing over and over. Now, let's make it personal. Def say hello, name, print fa there. Call it with say hello, Mishi. Shows hey there, Mishi. This shows how parameters let you pass data into a function. Let's dive into more. Functions can give back results with return. Check this out. Def add numbers a, b, return a plus b. This defines a function that adds 2 numbers. Call it with result equals add numbers 3, 4, and print f result. You get result 7. The return sends the answer back, so you can save or use it later, like in a game score. You can also handle more inputs. Def multiply numbers x, y, z, return x times y times z. Call it with product equals multiply numbers 2, 3, 4, and print f product gets product 24. This makes functions perfect for repeated math or tasks. Now let's explore defaults and flexibility. Add a default value. Def greet user, name code pilot, print f hello name. Call it with greet user, shows hello code pilot, or greet user Jake, shows hello Jake. This means you can skip the input if you want. Functions can also return multiple things. Def get details, return 25, Bali. Call it with age city equals get details and print f age city. Gets age 25, city, Bali. This is great for packing related data together. Time for a mini project, a calculator. Let's build it step by step. Start with def add calc num1 num2. Return num1 plus num2. Test it with sum result equals add calc 5 3 and print f sum result shows sum 8. Now add choices. Def calc all num1 num2 operation. If operation equals plus, return num1 plus num2. If operation equals minus, num2. If operation equals star, return num1 times num2. Else, return oops, operation not recognized. Pick plus, minus, or star. Test with diff equals calcall 5 3 and print f difference product prod. Gets difference 2 product 8. This shows how functions can handle multiple operations. Let's wrap up with tips. Keep functions small. Each should do one task, like add-in or greet-in. Use clear names like add calc instead of something vague. Avoid changing global variables inside unless you plan it. And test with big or negative numbers to catch bugs. This calculator can grow. Add division or a loop to keep asking for inputs. Practice, and you'll be writing reusable code like a pro. That's a wrap for Episode 7, Code Pilots. You've mastered functions and built a slick calculator. Next time, we'll ride into modules to organize your code. If you loved this, smash that like button, subscribe, and ring the bell. We're just getting started. Drop a comment if you've got questions, and I'll see you in Episode 8. Keep soaring, Code Pilots. Yo, Code Pilots, welcome back to Python from Zero to Hero, Episode 8. We've been riding through variables, conditionals, loops, lists, tuples, dictionaries, and functions, and now we're moving to modules. Modules are like your code organizers. They let you split your work into neat packages and reuse them anywhere. We'll learn what they are, how to make them, and even build a custom math tool to see them in action. So grab your hat, hit that like button if you're ready, and let's dive into this new adventure. Let's start with the big question. What are modules? Imagine your code is a big toolbox, and modules are the drawers where you keep your tools separate. In Python, a module is just a Python file with functions, variables, or classes you can reuse. Open VS Code and create two files, one called mymodule.py and another main.py. A module is like your code drawer, keeps functions and vars organized for reuse. Then type def say hi, print hi from my module. This is a function definition inside a module. Now, switch to main.py and import it with import mymodule. Then call mymodule.sayHi. You'll see hi from my module. This shows how modules let you organize and access code from another file, keeping everything tidy. Let's dig deeper. How do you use modules? You can import specific parts. Back in mymodule.py stores a number and a function to add two values. Add my variable equals 42 and def add nums ab, return a plus b. Save it in main.py. Import specific items from the module. Use from my module import add nums my variable. Now, call print add nums 53 gets 8 and print my variable gets 42. This way, you only grab what you need, save in memory. You can also use aliases with import mymodule as mm and call mm.sayHi. Same result. Modules are great for avoiding clutter and making your code reusable across projects. Now let's talk about built-in modules. Python comes with a bunch ready to use. One is the math module, perfect for calculations. In main.py, brings in Python's math tools for calculations. type import math and try print math scored 16. You'll get 4.0, the square root. Or use print math.py, gives you 3.14159, a constant. These built-in modules save you from writing complex math yourself. You can also import specifics, like from math import sin, cos, with import-specific math functions like sine and cosine. Test print sin math pi over 2 gets about 1.0. This shows how modules extend Python's power with pre-made tools. Time for a mini project, a custom math tool. Let's create a module for our own calculations. In mymodule.py, a function to square a number. Add def square num, return num times num. A function to cube a number. Add def cube num, return num times num times num. A constant value to use. Add myConstant equals 10. A function to raise a number to a power. Add def power, base, expand. Return base times expand. Save it. In main.py, use our custom math functions and constant. Use from mymodule, import square, cube, myConstant, power. Test with print square 4, get 16. Print cube 3 gets 27. Print myConstant gets 10. And print power 23 gets 8. This custom module lets you build and reuse your own math functions, making your code super flexible. Let's wrap up with some key points. Keep modules focused. Each should handle one area, like math or greetings. Name them clearly, like my module or math tools. Watch out for name clashes. If two modules have the same function, use aliases or full paths, like mymodule.addNums. Test your imports to ensure everything works. This math tool can grow. Add more functions like division or logs, or even share it with friends. Practice, and you'll be organizing code like a pro. That's a wrap for episode 8, Code Pilots. You've mastered modules and built a slick math tool. Next time, we'll gallop into file handling to save and load data. If you loved this, smash that like button, subscribe, and ring the bell. We're just getting started. Drop a comment if you've got questions, and I'll see you in episode 9. Keep soaring, Code Pilots. Yo, Code Pilots! Welcome back to Python from Zero to Hero, episode 9. We've journeyed through variables, conditionals, loops, lists, tuples, dictionaries, functions, and modules, and now we're tackling file handling. File handling is like giving your code a memory. It lets you save data to files and load it back whenever you want. We'll learn the basics, explore different ways to work with files, and build a note-saving project to put it all together. So grab your hat, hit that like button if you're excited, and let's get rolling. Let's start with the basics. What is file handling? It's how Python lets you interact with files on your computer, like saving a grocery list or reading a story. Open VS Code and create a file called main.py. First, handles opening and closing a file safely. Type with open notes text w as file, file.write hello code pilot. This opens a file named notes.txt in write mode. W writes a line and closes it automatically. Now, read it back with handles reading content from a file. Use with open notes.txt r as file. Content equals file.read and print content. You'll see hello code pilot. The with statement ensures the file closes properly, keeping your program safe and clean. Let's dive into file modes. There are different ways to open files. Write mode W creates a new file or overwrites it like before. Try it again with open notes text to queue as file and read it. Now it's new note here. Append mode A adds to the end instead. Use appends text without overriding. With open notes text as file write another line. The end starts a new line. Read it again, and you'll see new note here, another line. Read mode R is for view in only, which we did earlier. These modes give you control over how you handle files. Now, let's explore reading files in detail. You can read line by line. Use reads file line by line. With open notes.txt as file for line and file, print line strip. Strip removes extra spaces. If you added those two lines, it'll print each one separately. You can also read all lines into a list with reads all lines into a list. Use with open notes.txt as file, lines equals file.readLines, and print lines. Gets a list like new note here and another line. This is handy for processing file data step by step. Time for a mini project, a note-saving tool. Let's build it. Create main.py and add saves a new note to a file. With open notes.txt a as file, note equals input enter a note. File write full fn note. Run it. Type buy milk and check notes.txt. It's added. Now, add reads and displays all notes. With open notes.txt r as file, print your notes. For line and file, print line strip. Run it again, and it shows all notes. To clear the file, add clears the file content. With open notes.txt w as file write empty. This wipes it. This tool lets you save, view, and clear notes, making file handling practical. Let's wrap up with some tips. Always use with to avoid leaving files open. Check if a file exists before writing to prevent errors. Use import os and os.path.exists notes.txt. Don't write huge data in one go. Use append mode for big files. Test with different inputs like empty notes to catch issues. This note tool can grow, add dates, categories, or save to different files. Practice, and you'll be handling files like a pro. That's a wrap for episode 9, Code Pilots. You've mastered file handling and built a slick note-saving tool. Next time, we'll ride into error handling to make your code bulletproof. If you loved this, smash that like button, subscribe, and ring the bell. We're just getting started. Drop a comment if you've got questions, and I'll see you in episode 10. Keep soaring, Code Pilots. Yo, Code Pilots. Welcome back to Python from Zero to Hero. Episode 10. We've soared through variables, conditionals, loops, lists, tuples, dictionaries, functions, modules, and file handling. And now we're tackling error handling. Error handling is like your code safety net. It catches mistakes before they crash everything. We'll learn how to spot and fix errors and build a tough calculator to test it out. So grab your hat, hit that like button if you're ready, and let's dive in. Let's start with the basics. What's error handling? It's your way to deal with problems like dividing by zero or typing the wrong data. Open VS Code and create a file called main.py. Handles errors to keep code running smoothly. Add try, result is 10 divided by 0. Accept zero division error. Print, can't divide by 0. This tries the division, but if it fails, it prints a message instead of crashing. Run it, and you'll see can't divide by 0. The try block tests the code, and accept catches the error, keeping your program alive and user-friendly. Let's dig deeper. How do you handle different errors? Errors have specific types, like value error for bad input. Try catches invalid input errors. With try, number equals int, input enter a number. Print number. Accept value error. Print. That's not a number. If you type ABC, it catches the error and says that's not a number. You can catch multiple errors with multiple except blocks. Try handles division and input errors together. Add try. Num equals int, input, enter a number. Result equals 10 divided by num. Accept value error. Print, not a number. Accept 0 division error. Print, can't divide by 0. This covers both cases neatly. Now let's use else and finally for more control. The else runs if no error happens. Try runs code if no errors occur. With try, num equals int, input, enter a number. Result equals 10 divided by num. Accept value error. Accept 0 division error. Print can't divide by 0. Else, print result. If you enter 2, it shows result 5.0. The finally block always runs, even with errors. Adds cleanup code that always executes. Add finally, print, done calculating. It prints after every try, no matter what. This makes your code more robust. Time for a mini project, a robust calculator. Let's build it. Create main py and add builds a safe calculator with error handling. With while true, try. Num1 equals float input, enter first number. Num2 equals float input, enter second number. OP equals input, enter operation, plus, minus, or y. If OP equals divide by plus, result equals num1 divide by num2, equals num1 times num2, equals num1 plus num2, equals num1 plus num2, equals num1 minus num2. Else, raise value error, invalid operation. Accept value error as e, print, error. Accept 0 division error, print, error. Can't divide by 0. Else, print, result, result. Finally, print, ready for next calculation. Test it with 4.2 and divide by 0. Gets result 2.0. Try ABC, or it handles errors gracefully. This loop keeps it running. Let's wrap up with some tips. Use specific except clauses to catch exact errors, not just a general one. Add raise to throw custom errors if needed. Test with edge cases like negative numbers or empty inputs. This calculator can grow. Add more operations or save results to a file. Practice, and you'll be handling errors like a pro, making your code rock solid. That's a wrap for episode 10, Code Pilots. You've mastered error handling and built a tough calculator. Next time, we'll explore object-oriented programming to level up your skills. If you loved this, smash that like button, subscribe, and ring the bell. We're just getting started. Drop a comment if you've got questions, and I'll see you in episode 11. Keep soaring, Code Pilots. Yo, Code Pilots. Welcome back to Python from Zero to Hero, episode 11. We've mastered variables, conditionals, loops, lists, tuples, dictionaries, functions, modules, file handling, and error handling, and now it's time for our first big project, a number guessing game. This game will test your skills with loops, conditionals, and random numbers. We'll build it step by step, add features, and make it fun. So grab your hat, hit that like button if you're ready, and let's dive into coding. Let's start with the idea. The game picks a random number between 1 and 100, and you guess it. It tells you if you're too high or too low. We begin by bringing in a tool to generate that number. Think of it as a magic box for random choices. Then we set up a secret number that the game keeps hidden, using that tool to pick something between 1 and 100. We also start a counter to track how many guesses you make. The heart of the game is a loop that keeps going until you win, asking you to enter a number each time. Inside, it checks if your guess matches the secret number, and if it does, it celebrates your win and stops. If not, it lets you know if you're too low or too high, giving you a hint to try again. Give it a go by guessing a few times to feel how it guides you toward the answer. Now let's add a challenge. Let's limit it to 10 guesses. We start by setting a maximum number of tries to keep things interesting. The loop changes, so it only runs as long as you're under that limit, making each guess count. Every time you guess, the counter goes up, tracking your attempts. The win check stays the same, stopping the game when you get it right. But now, if you hit the maximum tries, it tells you the game's over and reveals the secret number. Try guessing wrong 10 times to see how it wraps up, adding that extra layer of excitement. Let's make it smarter by tracking the range of your guesses. We set a starting low point at 1 and a high point at 100 to frame the game. When you enter a guess, the prompt now shows that range to help you focus. If your guess is too low, the game updates the lowest possible number to just above your guess, narrowing the field. If it's too high, it adjusts the highest number to just below your guess, closing in on the target. This makes each try more strategic. Test it out by guessing 50, then 25 when it says too low, and 75 when it says too high, watching how the range tightens up. Let's keep the fun going by making it replayable. We set up a condition to ask if you want to play again at the start. A bigger loop wraps the whole game, running as long as you say yes, giving you a fresh start each time. Inside, we reset the secret number to a new random pick, clear the guess counter, and refresh the limits and range. After you win or lose, it asks if you want another round. Try winning, then type yes to play again, and enjoy the endless fun this adds to the game. Let's reward your skill with a score system. When you guess correctly, the game calculates a score based on how fast you got it, starting with a big number and subtracting points for each guess. If that score dips below 0, it caps at 0 to keep it fair. Then, it shares your score with a win message to celebrate. Give it a shot with 5 guesses to see a decent score, and try 10 guesses to see it hit 0, showing how speed pays off. Let's save your best moment by storing the high score in a file. We bring in a tool to check if a file exists, ensuring we can read or create it. If there's an old high score, it loads that number. If not, it starts at 0. After calculating your new score, it compares it to the high score. If you beat it, the game saves your new record to the file and announces your triumph. Otherwise, it reminds you of the current high. Test this by setting a high score, beating it, and checking the file to see your name in lights. Let's give you a helping hand with a hint system. We set a limit of 3 hints to keep it balanced. Inside the guessing loop, it asks if you want a hint before each try. If you say yes, it figures out the midpoint of the current range and suggests a number around there, then reduces your hint count. This gives you a clue without giving it all away. Try saying yes a few times to use your hints and see how they guide you closer. Let's spice it up with different difficulty levels. At the beginning, it asks you to pick a level. letting you choose how hard you want it. Depending on your choice, it sets a different number of guesses and a range for the secret number. Easy with more tries and a smaller range, medium as a balance, and hard with fewer tries and a bigger range. The game then picks a new secret number based on that level. Test each level to feel the shift in challenge, from easy to hard. Let's add some pressure with a timer. We bring in a time tool to track how long you take. The guessing loop now checks not just your guesses, but also if you're within a 60-second limit. If time runs out, it stops the game and reveals the number. Try guessing quickly within the time, or let it expire to see the cutoff in action, adding that rush to beat the clock. Let's make it welcoming with an intro screen. The game starts by printing a title to set the mood, then shows the range you're working with. It also displays how many guesses and seconds you get and mentions the hint option to prep you. Run it to see this friendly start, making the game feel more like a polished experience. Let's make sure it's solid by testing and fixing. Try entering something like 0 or letters to see if it handles bad input gracefully. Check what happens after the time runs out or when you use all your hints. We add a safety net to catch invalid numbers and keep the game going. Test these edge cases to ensure everything runs smoothly without crashing. Let's wrap up with some tips. Test every level and feature to catch any quirks. Save your high scores regularly to avoid losing them. You could even add sounds or graphics later with extra tools. This game has room to grow. Think multiplayer modes or leaderboards. Keep practicing, and you'll be on your way to becoming a game development star. That's a wrap for episode 11, Code Pilots. You've built an epic number guessing game. Next time, we'll create a to-do list manager. If you loved this, smash that like button, subscribe, and ring the bell. We're just getting started. Drop a comment if you've got questions, and I'll see you in episode 12. Keep soaring, Code Pilots. Yo, Code Pilots, we've just soared through the first part of Python from zero to hero. 1 hour journey across 11 amazing episodes. This summary will recap your wins. Practice projects, read books, or take courses. Set goals, like making a game or analyzing data, and track your progress. The Python community is huge, so lean on it to learn and share. That's a wrap for part 1. You've mastered the basics and built something amazing. Like this video, comment with your thoughts, and keep coding your own story. See you in the Python skies. Yo, Code Pilots! Welcome to part 1 of the Python OOP Masterclass, a journey into object-oriented programming. Today, we'll introduce classes, objects, and why OOP matters. Hit that like button, and let's start. Let's start with what OOP is. It's a programming paradigm where we organize code into objects, which are instances of classes. Think of a class as a blueprint, like a car design, and objects as the cars built from it. This approach makes code reusable, modular, and easier to manage, setting the stage for big projects. First, let's define a class. In Python, use the class keyword like class car. Inside, we can add attributes, data, and methods, functions. A simple attribute might be color equals red, and a method could be drive that prints a message. This is our first step into creating objects. To create an object, we instantiate the class with myCar equals car. This builds an instance based on the blueprint. We can access attributes with mycar.color or call methods with mycar.drive. This shows how classes turn into real, usable objects in your code. Let's add a constructor with init. This special method runs when an object is created, letting us set initial attributes. For example, def init self-color. Self-color equals color lets us do mycar equals car. It's key for customizing objects right away. Now, let's use methods. Define a method like def_drive self. Print the self-color car is driving. The self parameter refers to the instance, linking attributes and methods. Call it with mycar.drive, and you'll see the color in action. Try it to see the output. Let's explore attributes more. We can have instance attributes set in init, like self.speed equals 0, or class attributes shared by all instances, like car.brand equals Toyota. Access them with mycar.speed or car.brand to understand their scope in a class. Time for a practical example. Let's build a dog class with init self, name, breed, and a method bark, self. Create my dog equals dog max, golden, and call my dog bark. This real-world object shows how classes model entities with behavior. Let's test our classes. Run my car drive and my dog bark to see the outputs. Change my car.color to green and call drive again. This hands-on practice helps you see how objects behave and how to tweak them. Classes are the foundation of OOP. They let you group related data and functions, making code cleaner than using standalone functions. This modularity is why OOP is used in games, apps, and more. Start thinking of objects as your building blocks. Let's think about next steps. We'll dive into inheritance and encapsulation soon, building on these basics. Practice creating your own class, like a book, to get comfortable, experiment, and have fun. That's a wrap for Part 1. Code Pilots, you've started your OOP journey. Like this, subscribe, and share your class ideas below. See you in Part 2. Keep coding. Yo, Code Pilots! Welcome to Part 2 of the Python OOP Masterclass. Last time, we started with classes, and now we'll master constructors and methods. Hit that like button, and let's dive in. Let's recap and focus on constructors. The init method is a special constructor that runs when an object is created. It lets us initialize attributes, like setting a car's color or model, making each object unique right from the start. Let's explore this further. Let's create a car class with a constructor. Use def init self color model to set self color and self model. This allows us to instantiate with mycar equals car red Toyota, giving us control over initial values for each instance. Now let's add a method to the car class. Define def describe to print the car's details, like print f self color, f self model car. Methods are functions inside a class that operate on the object's data. Call it with myCarDescribe to see it work. Let's make the method interactive. Add def change color self new color to update self.color and print a confirmation message like printf color change to self color. Test it by calling myCarChangeColor blue and observe the change. Time for a practical example with a student class. Use init self name grade to set initial attributes like self-name and self-grade. Then add def study to print a message like print f self-name is studying. Create my student equals student Ali 10. Let's enhance the student class with a method. Add def update grade. Call it with myStudent.UpdateGrade11 and check the output to see the validation in action. Now, let's add another method. Define def getInfo to return a formatted string like return f, self-name, grade, etc. Call print myStudent.getInfo to display the student's details in a clean format. Let's test edge cases. Modify update grade to reject invalid inputs like negative grades with an if statement. Try myStudent.UpdateGrade-1 and see how the method handles it, ensuring data integrity. Methods can call each other for efficiency. Add def promote to increment self-grade by 1 and call update grade if the new grade is valid. Use myStudent.promote to see how methods collaborate within the class. Let's add flexibility with a parameterized method. Define def greet self message to print f self-name says. Now call it with myStudent.greet hello to see how it adapts to different inputs. That's a wrap for part 2. Code pilots, you've mastered constructors and methods. Like this, subscribe, and experiment with your own methods. See you in part 3. Keep coding. Yo, code pilots. Welcome to part 3 of the Python OOP Masterclass. We've built a foundation with classes and methods. And now we're diving into properties and practical coding. This will be detailed, so hit that like button and let's get started. Let's start by understanding properties in Python. Properties are a way to control attribute access using decorators like @property. They let us add logic, such as validation or computation, before getting or setting a value, acting as a gatekeeper for your object's data. This is different from direct attribute access, and we'll explore it step by step with examples to make it clear. To begin, let's create a car class. Define it with def initSelfSpeed to set an initial speed attribute. Then use @property with def speed self to return self_speed, using the underscore to indicate it's protected. Instantiate it with myCar equals car 100. Let's set this up and move to the next step. Now let's test this setup. Create myCar equals car 100 and run print myCar speed to see the initial speed. This shows how the @property decorator lets us access speed like an attribute. Take a moment to observe the output, and let's discuss why this is useful before adding more. Next, let's add a setter. Use @speed.setter with def speed self value to check if value is greater than 0 before assigning it to self_speed. This prevents invalid speeds. Update the class with this setter. Let's add it and prepare to test it. Let's test the setter with myCar equals car 100. Try myCar.speed equals 120. To increase speed, then myCar.speed equals -10 to test the validation. Run print myCar.speed after each to see the results. This shows how the setter protects the attribute. Take time to understand the output. Now, let's add a deleter. Use @speed.deleter with def speed.reset self._speed to 0. Add this to the car class. Let's include it and move to testing. Test the deleter. Create myCar equals car with 100. Set mycar.speed equals 150. Then use del mycar.speed and check with print mycar.speed. This demonstrates the full life cycle of a property. Pause here to see how it resets and why it's helpful. Let's move to a bank account class. Start with def__init _self balance to set self._balance and add @property with def balance self to get it. Create my account equals bank account with 1000. Let's set this up and test it next. Test the bank account setup. Run print my account balance to confirm the initial balance of 1000. This shows the getter in action. Take a moment to explore the output and get comfortable with this structure. Add a setter for balance. Use @balance.setter with def balance self amount to update self_balance if amount equals 0. Add this to the class. Let's include it and prepare to test. Test the balance setter with my account equals bank account 1000. Try my account.balance equals 1500 to deposit. Then my account.balance equals -500 to test validation. Check with print my account.balance. Discuss how this prevents negative balances. Let's add a withdrawal method. Define def withdraw self amount to subtract from self balance if amount is 0 and funds are sufficient. Add this. Let's include it and test it next. Test the withdraw method with my account equals bank account 1000. Run my account withdraw 300 and check print my account balance. This shows the method working with the property. Take time to see the new balance. Add error handling to withdraw. Modify it to raise a value error if amount is negative or exceeds balance. Update the class. Let's add this and test it. Test the error handling. With my account equals bank account 700, try my account withdraw 2000 and observe the value error. This protects the account. Discuss the error and its importance. Let's create a game character class. Use def init self health for self_health and add @property with def health to get it. Create mychar equals game character 100. Set this up and test next. Test the game character setup. Run print mychar health to see the initial health. This establishes the base. Take a moment to get familiar with it. Add a setter for health. Use @health setter with def health self value to set self_health if 0 equals value equals 100. Add this. Let's include it and test. Test the health setter with mychar equals game character 100. Try mychar health equals 80, then mychar health equals 150. Check with print add a take damage method. Define def take damage self damage to reduce self_health if the result is non-negative. Add this. Let's include it and test. Test take damage with mychar equals game character 100. Set mychar health equals 90, then mychar take damage 40, and check print mychar health. Discuss the result. That's a wrap for part 3, Code Pilots. You've mastered properties in practical coding with thorough testing. Like this, subscribe, and practice these concepts. See you in part 4. Keep coding. Yo, Code Pilots. Welcome to part 4 of the Python OOP Masterclass. We've covered properties, and now we're diving deep into inheritance. This will be detailed, so hit that like button and let's get started. Let's begin with what inheritance is. Inheritance is a core concept in OOP where a child class can inherit attributes and methods from a parent class. Think of it like a family tree. A car can inherit from a vehicle class. Reusing code and building on it. This reduces redundancy and sets up a hierarchy, and we'll explore this with car examples. First, let's create a vehicle parent class. Define it with def init self speed to set self.speed, and add a method def move to print vehicle is moving. This will be the base class for our car-related examples. Let's set it up and move forward. Let's test the vehicle class. Create myVehicle equals vehicle 60 and run myVehicle move to see the output. This gives us a starting point. Take a moment to observe the result and understand the parent class's role. Now let's create a car child class that inherits from vehicle. Use class car vehicle and add def init self speed brand to set self brand while calling the parent's init with super init speed. This links the child to the parent. Let's add it and test next. Test the car inheritance. Create my car equals car 100 Toyota. Run my car move to use the inherited method and print my car speed to check the inherited attribute. Take time to see how the child class builds on the parent. Discuss the output. Let's add a specific method to car. Define def honk self to print beep beep from self brand. This adds unique behavior to the child class. Let's include it and prepare to test. Test the honk method. With my car equals car 100 Toyota, run mycar.honk to hear the car's sound. This shows how the child can extend the parent. Pause to explore this new feature. Let's create another child class, sports car, inheriting from car. Use class sports car car with def init self speed brand top speed to set self.topspeed, calling super init speed brand. This creates a multi-level inheritance. Let's add it. Test the sports car class. Create my sports car equals sports car 200 Ferrari 300 and run mysportscar.move for the inherited move. Print mysportscar.speed for the car speed and print mysportscar.topspeed for the new attribute. Take time to see the hierarchy. Let's override the move method in sports car. Define def move to print sports car print is racing at self speed kilometers per hour. Update the class. Let's include it and test next. Test the overridden move in sports car. With my sports car equals sports car 200 Ferrari 300. Run mysportscar.move to see the racing message. This shows how a grandchild can customize behavior. Discuss the output. Let's add a practical example with a garage class. Use def init self to hold a list of vehicles and def add vehicle to add any vehicle object. Add some car and sports car instances. Let's set this up. Test the garage class. Create garage equals garage. Add my car and my sports car with garage.addVehicle, my car, and garage.addVehicle, my sports car. Then print the list. This shows inheritance in a real-world context. Take time to explore. Let's enhance garage with a display all method. Define it to loop through vehicles and call move on each. Update the class. Let's add it and test. Test the display all method. Run garage display all to see all vehicles move. This demonstrates how inheritance allows a uniform interface. Pause to analyze the result. Let's add a speed check to display all. Modify it to print only vehicles with speed greater than 100. Update and test. Discuss how inheritance supports this filtering. That's a wrap for Part 4. Code pilots, you've mastered inheritance with car examples. Like this, subscribe, and try your own inheritance trees. See you in Part 5. Keep coding. Yo, code pilots. Welcome to Part 5 of the Python OOP Masterclass. We've mastered inheritance, and now we're exploring polymorphism. This will be a deep dive with lots of explanations. So hit that like button, and let's get going. Let's talk about what polymorphism is and why it's exciting. Polymorphism means many forms. It lets objects of different classes be treated as instances of a common parent class, even if they behave differently. Imagine a garage where all vehicles, cars, trucks, can move, but each does it its own way. This flexibility is powerful because it lets us write code that works with any child class without knowing its type ahead of time. Today, we'll see how this works with our car examples. So let's think about why this could make our programs more adaptable. To start, let's recall our vehicle class from last time, which has a move method. We're going to use it as the parent class again. The idea here is to let different types of vehicles inherit from it, but each can redefine move to suit itself. This is the foundation of polymorphism, and it's worth taking a moment to appreciate how it sets up a shared interface. Let's set the stage by looking at that class again. Now let's think about why we want to use polymorphism. Imagine you're building a racing game where different cars need to move differently. A regular car cruises. A sports car races. Instead of writing separate code for each, polymorphism lets us use one function to handle all types. This saves time and makes the code easier to maintain. So let's create a car class again, inheriting from vehicle, and we'll add a custom move. Let's plan this out before jumping in. Let's build the car class. We'll use class car vehicle with def init self speed brand to set self brand and call super init speed. Then let's override move to print something like car self brand is cruising at self speed kilometers per hour. The goal here is to show how the child can change the parent's behavior. Let's add this and take a breath to see what we've done. Before we test, let's discuss what we're achieving. By overriding move, we're giving car its own identity, while still fitting into the vehicle family. This is the heart of polymorphism. Different forms under one roof. Now let's test it. Create my car equals car 100 Toyota and run mycar.move to see the cruising message. Take a moment to watch the output and think about how this differs from the parent. Let's add another vehicle type to see polymorphism in action. We'll create a sports car class, also inheriting from vehicle, with def init self speed brand top speed and a move method that prints sports self brand is racing at self speed kilometers per hour. The reason we're doing this is to show how multiple classes can offer different behaviors under the same method name. Let's set this up. Let's test the sports car too. Create my sports car equals sports car 200 Ferrari 300 and run my sports car.move to see the racing message. This reinforces our point. Both car and sports car use move, but each does it differently. Pause here to let that sink in, and think about the flexibility this gives us. Now let's talk about why a function can treat these differently. We'll create a moveVehicle function that takes any vehicle object and calls move. The beauty here is that it works for any child class without us needing to check its type, saving us from writing repetitive code. Let's add this function and plan how we'll test it. Let's test moveVehicle. Define def moveVehicle, vehicle.move, then call it with moveVehicle, my car, and moveVehicle, my sports car. Watch the different outputs. This is polymorphism at work. The function doesn't care which vehicle it gets. It just triggers the right behavior. Take time to discuss why this is a game changer for coding. Let's apply this to a practical example. We'll use a racetrack class with a method startRace that takes a list of vehicle objects and calls move on each. This mimics a real scenario where different cars race in their own style. Let's set this up and think about how it leverages polymorphism. Test the racetrack. Create racetrack equals racetrack. Add my car and my sports car to a list. And run racetrack.startRace with my car and my sports car. See how each vehicle moves differently. This shows polymorphism in a race context. Pause to explore the result. Let's enhance startRace to declare a winner based on speed. Modify it to find the fastest vehicle and print the result. This adds a practical twist. Let's update and test it to see who wins. Test the winner feature. Run the race again and check the output to see the fastest vehicle. This wraps up how polymorphism, combined with inheritance, powers dynamic applications. Take a moment to reflect on this. That's a wrap for Part 5, Code Pilots. You've mastered polymorphism with car examples. Like this, subscribe and experiment with your own polymorphic designs. See you in Part 6. Keep coding. Yo, Code Pilots. Welcome to Part 6 of the Python OOP Masterclass. We've covered polymorphism, and now we're diving into abstraction. This'll be a detailed journey with lots of explanations, so hit that like button and let's get started. Let's unpack what abstraction is and why it's a big deal. Abstraction is all about hiding complex details and showing only the essentials to the user. Think of a car. When you drive, you don't need to know how the engine works. You just press the pedal. In coding, this means creating classes that expose simple interfaces while keeping the messy stuff hidden. It makes code easier to use and maintain. And today, we'll explore this with our car theme. Let's talk about why to get started. Let's think about why abstraction matters. Imagine you're building a system with lots of vehicle types: cars, trucks, buses. Without abstraction, users might accidentally mess with internal engine details, causing errors. Abstraction lets us define what users can do, like start or stop, without exposing how it's done. We'll use the vehicle class as a base and add abstraction tools. Let's take a moment to appreciate how this simplifies things before we begin. In Python, we can use the ABC module for abstraction, which stands for Abstract Base Classes. This lets us create a blueprint that forces child classes to implement certain methods. The goal here is to ensure every vehicle has a start engine method, but we won't define how. It's up to the child. Let's import ABC, create an ABC class called vehicle, and add an abstract start engine method. Let's plan this out carefully. Let's build the abstract vehicle class. Use from ABC import ABC abstract method, then class vehicle ABC. with @abstract method over def start engine self pass. This tells Python this is a blueprint. Child classes must fill in the details. The reason we're doing this is to enforce a standard across all vehicles. Let's add it and discuss what it means. Before moving on, let's talk about the power here. By making start engine abstract, we're saying every vehicle must have this ability, but the implementation can vary. This protects our code from incomplete designs and makes it more robust. Now, let's test this setup by trying to create a vehicle instance. Spoiler, it won't work. Let's see the error and understand why. Since we can't instantiate vehicle, let's create a car class that inherits from it. Use class car vehicle and implement def start engine self to print car engine starting with a roar. The purpose is to show how a child fulfills the abstract requirement. Let's add this and prepare to test. Let's test the car class. Create myCar equals car and run mycar.startEngine to see the message. This works because car provided the missing piece. Take a moment to see the output and think about how abstraction guides us. Let's also discuss why this prevents someone from using an unfinished class. Let's add a sports car class to see more variety. Use class sports car vehicle with def start engine to print sports car engine revving at high RPM. The idea is to show different implementations while sticking to the abstract rule. Let's set this up. Test the sports car class. Create mySportsCar equals sports car and run mySportsCar.startEngine to see the revving message. This highlights polymorphism within abstraction. Pause to reflect on how both classes meet the same standard differently. Now let's think about a practical use. We'll create a garage class with a method startAllVehicles that takes a list of vehicle objects and calls startEngine on each. This leverages abstraction to manage any vehicle type. Let's plan this out and add it. Test the garage class. Create garage equals garage. Add myCar and mySportsCar and run garage.startAllVehicles, myCar, mySportsCar. Watch the different start messages. This shows abstraction in action. Let's discuss why this makes the garage code flexible. Let's enhance startAllVehicles to check if each vehicle starts successfully. Add a simple condition, like printing a confirmation. Update it. Let's test and talk about how abstraction helps us add features without breaking the system. Test the enhanced startAllVehicles. Run it again and see the confirmations. This wraps up how abstraction simplifies complex systems. Take a moment to appreciate the elegance of hiding details. That's a wrap for Part 6, Code Pilots. You've mastered abstraction with car examples. Like this, subscribe and try applying abstraction in your projects. See you in Part 7. Keep coding. Yo, Code Pilots. Welcome to Part 7 of the Python OOP Masterclass. We've covered abstraction, and now we're diving into encapsulation. This will be a thorough session with plenty of explanations, so hit that like button and let's get going. Let's start by understanding what encapsulation is and why it's a game changer. Encapsulation is about bundling data and the methods that operate on that data into a single unit, while also controlling access to it. Think of a car's dashboard. You can turn the key, but you can't directly mess with the engine's wiring. In coding, this protects the internal state of an object from outside interference, making our programs safer and more reliable. Hey, have you ever wondered why some apps crash when you tweak the wrong setting? That's where encapsulation comes in to save the day. let's talk about why this matters for keeping things organized. So why do we need encapsulation? Imagine you're working on a team and someone accidentally changes a car's speed to a negative number, breaking the logic. Encapsulation lets us hide that speed value and only allow controlled changes through methods. This reduces errors and keeps the code's integrity intact. Oh, and here's a practical tip. In real projects, this also helps when you need to debug. Knowing data changes only happen through specific methods makes tracking issues way easier. We'll use our vehicle class to explore this. Let's take a moment to think about how this could save us from chaos. In Python, we achieve encapsulation using naming conventions like single or double underscores. A single underscore, for example, underscore speed, suggests it's protected, while a double underscore, example, underscore speed, makes it private with name mangling. The goal here is to control access, not just hide it. Hey, did you know this is super useful when you're sharing code with others? It sets clear boundaries. Let's create a vehicle class with a protected speed and a method to modify it. Let's plan this out with care. Let's build the vehicle class. Use class vehicle with def init self speed to set self underscore speed and add def set speed self speed to check if speed equals 0 before updating. The reason we're doing this is to ensure the speed stays valid. Oh, and a quick tip. Always add these checks in real code to avoid sneaky bugs. Let's add it and discuss how this protects the data. Before testing, let's talk about what we've gained. By using speed and a setter, we're telling other parts of the code not to touch the speed directly, only through our method. This is encapsulation in action, giving us control. Hey, in a real project, this could prevent a teammate from accidentally crashing your app. Pretty cool, right? Now, let's test it. Create myVehicle equals vehicle 60 and try myVehicle.setSpeed 80 to see it work. Then myVehicle.setSpeed -10 to catch the validation. Let's watch the result. Let's add a car class to see encapsulation in a child. Use class car vehicle with def initialize speed brand, calling super.initialize speed and setting self brand. Add a private fuel level with a method def add fuel self amount to update it if amount is 0. The purpose is to show layered protection. Oh, and here's a practical note. Using private variables like fuel level is great when you want to hide sensitive data, like a game's health points. Test the car class. Create myCar equals car 100 Toyota. Run myCar set speed 120 for the inherited method, and myCar add fuel 50 to check the fuel. Then try myCar add fuel -5 to see the limit. This shows how encapsulation works across inheritance. Pause to explore the outputs. Hey, notice how this keeps the car's fuel from going negative? That's encapsulation protecting us. Let's discuss why this is powerful. With underscore fuel level, even if someone knows the name, Python's name mangling, e.g. /car underscore fuel level, makes it hard to access directly. This adds a layer of security. Let's try accessing underscore grand and underscore fuel level directly to see what happens. Oh, and a tip. In real code, always document these private attributes to avoid confusion for your team. Before we move on, let's think about a practical angle. Encapsulation isn't just about hiding, it's about controlling how data evolves. For example, you could add a method to check fuel before starting the car, ensuring it won't stall. That's a real-world use case. Let's test accessing those attributes and talk about the results. That's it for the core concepts. We've seen how encapsulation bundles and protects data with our car examples. Hey, next time you're coding, try adding a setter with validation. It'll save you from headaches. Let's wrap up by testing those direct accesses. That's a wrap for Part 7, Code Pilots. You've mastered encapsulation with car examples. Like this, subscribe, and practice protecting your code. See you in Part 8. Keep coding. Yo, Code Pilots. Welcome to Part 8 of the Python OOP Masterclass. We've covered encapsulation, and now we're exploring composition. This will be detailed, so hit that like button and let's dive in. Let's start with what composition is. Composition is a way to build complex objects by combining simpler ones, like assembling a car from an engine and wheels. Unlike inheritance, it focuses on has-a relationships rather than is-a. This makes code more flexible and reusable. It helps avoid deep inheritance trees. Let's see why this could simplify our projects. Why use composition? It lets us swap parts easily. If a car needs a better engine, we just replace it without rewriting the whole class. This is handy in real-world scenarios like modular design. We'll use a car with an engine to explore this. Let's think about how this differs from inheritance. Let's create an engine class first. Use class engine with def init self power to set self power and def state self to print engine starting with self.power HP. The def init syntax here initializes the object with a power value. Let's include it. Now let's build a car class using composition. Use class car with def underscore init self brand engine to set self brand and self engine equals engine. Add def start self to call self engine start. The self engine assignment composes the car with an engine object. Let's add this. Let's consider the benefit. Composition lets us change the engine type without altering car. A practical edge over inheritance. We can test this later with different engines. Let's move forward with the concept. Let's add a wheel class. Use class wheel with def init self size to set self size and def rotate self to print wheel rotating at self size inches. The def init syntax sets up the wheel size. Let's add it. Update car to use composition with wheels. Add a list self.wheels equals wheel 16 for underscore init. The list comprehension here creates 4 wheels. The for underscore in range for loop iterates 4 times without using the variable. Let's set this up. Let's add a drive method to car. Use def drive with self to call self.wheels rotate. The dot notation self.wheels accesses the first wheel. Let's include it. Let's enhance engine with a stop method. Use def stop self to print engine stopped. This simple method adds more functionality. Let's add it. Update car to use stop. Add def stop to call self engine dot stop. The dot notation self engine dot stop accesses the composed objects method. Let's include it. Let's reflect on the flexibility. Composition shines when you need to test parts separately or swap them, like changing an engine. That's a wrap for Part 8, Code Pilots. You've mastered composition with car examples. Like this, subscribe, and try building with composition. See you in Part 9. Keep coding. Yo, Code Pilots! Welcome to Part 9 of the Python OOP Masterclass. So hit that like button and let's dive in. Let's start with what solid principles are. Solid is a set of 5 design guidelines. single responsibility, open-closed, Liskov substitution, interface segregation, and dependency inversion that help write better, maintainable code. They build on what we've learned, like encapsulation and composition. Let's see why these principles can make our car code more robust. Why use solid? These principles prevent common issues like tight coupling or hard-to-extend code. For example, a car system should be easy to update without breaking everything. We'll apply them step by step with our car example. Let's think about how they fit into our journey. Let's tackle single responsibility first. This means a class should have one job. Our car class might handle driving and fuel, which is too much. Let's create a fuel system class with def init self to set self.level equals 0 and def add fuel self amount to update if amount greater than 0. Note that def init initializes the object. Update car to use fuel system. Use self.fuelSystem equals fuel system in init and call self.fuelSystem.addFuelAmount in a new refuel method. The dot notation self.fuelSystem composes the system. Let's add this. Let's apply open-closed next. This says classes should be open for extension but closed for modification. Add a start method to fuel system to check self.level greater than 0. The if statement here handles the condition. This lets us extend behavior without changing existing code. For Liskov substitution, ensure a child class can replace a parent without issues. Create a sports fuel system inheriting from fuel system with a custom start. Use super.init to call the parent's init, a syntax for inheritance. Update car to accept any fuel system. Change init to self.fuelSystem equals fuel system. This uses a parameter for flexibility. Let's add this to support substitution. Let's move to interface segregation. This suggests small, specific interfaces. Define an iVehicle class with addAbstract method def drive self from ABC. The addAbstract method decorator marks it as abstract. Implement iVehicle in car with def drive self to print car is driving. The def here fulfills the interface. Let's include it. Finally, dependency inversion. This says high-level modules shouldn't depend on low-level ones directly. Use iVehicle in a race class with def start race self vehicle iVehicle. The type hint vehicle iVehicle specifies the dependency. That's a wrap for Part 9, Code Pilots. You've mastered solid principles with car examples. Like this, subscribe, and apply these in your code. See you in Part 10. Keep coding. Yo, Code Pilots! Welcome to Part 10 of the Python OOP Masterclass. We've mastered OOP concepts, and now it's time for a final project, a library management system. This will be detailed and exciting, so hit that like button and let's dive in. Let's set the scene for our project. We're moving away from cars to build a library management system using inheritance, polymorphism, abstraction, encapsulation, composition, and solid principles. Imagine a digital library where books are tracked, borrowed, and returned, with librarians managing it all. This project will showcase all we've learned, and I'll explain every step deeply: attributes, methods, public versus private, and why our design choices matter. Let's plan a system that's both functional and well-structured. First, let's define our base class with abstraction. We'll use from ABC, import ABC, abstract method. ABC is for abstract base classes, and @abstract method enforces method implementation. Create class item ABC with @abstract method def get info pass. The pass keyword is a placeholder, ensuring child classes define this method. This abstraction hides implementation details, like how each item's info is formatted, which is crucial for a scalable design. Let's create a book class inheriting from item. Use class book item. The parentheses show inheritance. Add def init, self, title, author, ISBN. Self underscore title equals title, self author equals author, self ISBN equals ISBN, the single underscore. Suggest protected attributes, a form of encapsulation. Implement def info, return f. Let's add composition with a library class. Use class library. With def init, self underscore items equals underscore. The list self items stores all items, again using underscore for protection. Add a public add item method. Def add item item append. This append method adds to the list, and this method's public nature allows external addition of items. A deliberate design choice for usability. Let's apply encapsulation with a private status. In book, add self underscore available equals true in init. The double underscore uses name mangling to hide this attribute, preventing direct changes. Add a public borrow method. Def borrow self, if self underscore available equals false, return true. The if checks availability, and return sends the result, showing controlled access, which is key for data integrity. Let's use polymorphism with a magazine class. Use class magazine item with def init self title issue. Self underscore title equals title. Self underscore issue equals issue. And override def get info self return f the title issue issue. This different implementation showcases polymorphism, letting each item type format its info uniquely. The override is a public method, intentional for consistency. Add abstraction with a borrowable interface. Use class borrowable ABC with @abstract method def borrow self pass and @abstract method def return item self pass. These abstract methods enforce borrowing logic. In book, implement def return item self underscore available equals true. The assignment updates the private state, fulfilling the interface. Let's apply Solid's single responsibility. Create a librarian class with def init self name. Self underscore name equals name. And def manage borrow self item return item borrow. This class handles borrowing, not item details, adhering to one responsibility. The dot notation item borrow calls the method, a public interface choice. Use dependency inversion with a library system class. Use class library system with def init self librarian. Self librarian equals librarian. The parameter librarian injects the dependency. Add def process borrow self item return self librarian manage borrow item. The type hint could be added, but we'll keep it simple, decoupling high level from low level. Let's explain the design. Attributes like underscore title are protected for internal use. Underscore available is private for safety. And public methods like getInfo provide access. Every choice, from abstract method to private attributes, supports maintainability. Let's appreciate the depth. That's a wrap for Part 10, Code Pilots. You've built a library system and mastered OOP. Like this, subscribe and tackle your own projects. See you in Part 11. Keep coding. Yo, Code Pilots! Welcome to Part 11 of the Python OOP Masterclass. We've reached the end of our OOP journey, and this is our final recap and send-off. This will be a heartfelt session, so hit that like button and let's wrap up together. Let's start with a big congratulations. You've come a long way, from understanding classes and objects to mastering inheritance, polymorphism, abstraction, encapsulation, composition, and solid principles. We built projects like the car simulation and library system, applying each concept step by step. This part is about reflecting on that journey, celebrating your growth, and looking ahead. I'll dive deep into what we've achieved and why it matters for your coding future. Let's take a moment to feel proud. Let's revisit inheritance. It let us create hierarchies, like vehicle to car, reusing code efficiently. The syntax, class child parent, was our foundation. And super, which calls the parent's method, helped manage initialization. This built a structure where child classes could extend behavior, a powerful tool for scalability that you can use in any project. Next, polymorphism gave us flexibility. Overriding methods like drive in different classes allowed varied behaviors under the same interface. The def keyword with a redefined method was key, enabling dynamic dispatch. This adaptability is what makes OOP dynamic, and it's something you can apply to customize software for different needs. Abstraction hid complexity with abstract base classes. Using from ABC import ABC, abstract method and @abstract method def method pass ensured a blueprint that child classes followed. The pass acted as a placeholder, enforcing structure without implementation, perfect for designing systems where details can evolve. Encapsulation protected data with access control. Attributes like self_private used double underscores for name mangling, while self_protected suggested caution. Methods like getters and setters, defined with DEF, controlled access, ensuring data integrity, a critical skill for secure coding. Composition built objects from parts. Solid principles tied it all together. Single responsibility kept classes focused. Open-closed allowed extension without change. Liskov substitution ensured substitutability. Interface segregation broke interfaces into small pieces. And dependency inversion decoupled dependencies. Now, let's look ahead. You're ready for advanced topics like design patterns, frameworks, or even game development with Pygame. Practice by building your own projects, maybe a school management system or a game. The skills you've gained, from super to solid, are your toolkit for the future. Before we go, a huge thank you. Your support, questions, and engagement made this journey amazing. This isn't goodbye, it's a see you later. Subscribe, check the playlist for review, and share your projects with me. You're now a code pilot ready to soar. That's a wrap for part 11, Code Pilots. You've conquered OOP. Like this, subscribe, and keep coding. Until next time, take off. Yo, Code Pilots, welcome to part 1 of the Python Masterclass, Data Structures. This series focuses on how to organize and manage data efficiently. Before we start, a quick note. I've covered Python basics like variables, loops, and data structures, list, tuple, dictionary, set, plus OOP concepts like classes and inheritance in separate videos. If you haven't seen them, check out the playlist link to get up to speed. Now, let's dive in. Let's begin with what data structures are. Data structures are ways to organize and store data, like lists or stacks, to make it easy to access and use. They're the foundation of efficient programming, helping us solve problems faster. This series will take you through various structures and their applications. So, let's explore why they matter. Why are data structures important? Imagine building a game. Structures like arrays help manage player stats, while stacks can handle game states. In any app, choosing the right structure saves time and resources. Python's flexibility, combined with our use of Jupyter Notebook, makes learning these concepts practical and hands-on. Let's see what's ahead. We're using Jupyter Notebook for this journey, where we'll write and test code interactively. In the first cell, type print hello data structures and press Shift-Enter to run. You'll see the output below. This setup lets us experiment live. Let's break down this process. Let's try a simple data structure. In a new cell, type mylist equals 123 and run it. This is a Python list, a basic structure we'll build upon. Add print mylist, you'll see 123. Lists are flexible, but we'll explore more specialized structures soon. This is our starting point. Let's discuss its role. Now, let's touch on how data structures work with functions. Add this code. Def add numbers AB, return A plus B, and run it. Call it with print add numbers 23. Output is 5. This shows how we can manipulate data, a key idea we'll expand on. The syntax is simple. Let's see why this matters. To wrap up the intro, we've covered what data structures are, their importance, and started with Jupyter Notebook. We tested a list and a basic function, giving you a taste of what's coming. This series will cover stacks, queues, linked lists, and more, with hands-on examples. Let's prepare for the next step. That's it for Part 1, Code Pilots. You've started your data structures journey. Like this, subscribe, and practice with lists and functions. Next time, we'll dive into arrays. See you then, and keep coding. Yo, Code Pilots! Welcome to Part 2 of the Python Masterclass, Data Structures. Last time, we introduced the basics, and now we're diving into arrays. If you missed the Python and OOP basics, check the playlist link. Let's get started. Let's talk about what arrays are. An array is a linear data structure that stores elements of the same type in contiguous memory locations. This makes accessing elements by index fast, but it has limits like fixed size in some languages. In Python, we use lists as a flexible version of arrays. This episode explores their concepts and how to implement them. Let's dig in. Why are arrays important? They're the foundation for many data structures and algorithms. For example, in a game, an array can hold player scores, and searching or sorting relies on them. Python's lists act like dynamic arrays, growing as needed, which we'll see in action. We're using Jupyter Notebook to make this interactive. Let's start coding. In a new Jupyter cell, type myArray equals 10, 20, 30, 40, and run it with Shift-Enter. This is a basic array using a Python list. Add print myArray. You'll see 10, 20, 30, 40. This shows how we can store data sequentially. Let's break down how indexing works. Try print myArray 1 for 20. Let's add and modify elements. In a new cell, use myArray.append 50 to add 50 and run. Then print myArray shows 10, 20, 30, 40, 50. To change an element, try myArray 0 equals 5 and print again. Now it's 5, 20, 30, 40, 50. This flexibility is a Python list feature. Let's discuss its implications. Now, let's explore limitations. Add myArray 5 equals 60 and run. It errors because we're out of bounds. Unlike static arrays in C, Python lists handle this by resizing, but accessing invalid indices fails. This shows a trade-off. Let's compare it with a fixed-size approach using NumPy. Import NumPy as np, fixed array, equals np array, 1, 2, 3. Let's try a function to work with arrays. In a new cell, type def sum array, total equals 0. For num in R, total plus equals num, return total. Print sum array my array. Run it. Output is 195. 5 plus 20 plus 30 plus 40 plus 50. This simple algorithm sums elements, showing how arrays support operations. Let's analyze its logic. To wrap up, we've covered what arrays are, their implementation with Python lists, and a basic function. We saw flexibility with lists and a glimpse of NumPy for fixed arrays. This sets the stage for stacks and queues next. Arrays are a starting point for more complex structures. Let's prepare for the journey ahead. That's it for Part 2, Code Pilots. You've learned about arrays and coded them. Like this, subscribe, and practice with lists and the sum function. Next time, we'll explore stacks. See you then, and keep coding. Yo, Code Pilots! Welcome to Part 3 of the Python Masterclass, Data Structures. We've covered arrays, and now we're stepping into the world of stacks. If you're new here, I've explained Python Basics and OOP in separate videos. Head to the playlist to get the foundation. Let's dive into this stack of knowledge with excitement. Let's start by understanding what a stack is. A stack is a linear data structure that follows the LIFO principle, last in, first out. Imagine a real-life stack of plates on a table. You place a new plate on top, and when you need one, you take it from the top too. In programming, this means the last element added is the first to be removed. A stack has two core operations: push, which adds an element to the top, and pop, which removes the top element. There's also an optional check, like is empty, to see if the stack has any items. This structure is super useful because it mimics how we often handle tasks, where the most recent action needs attention first, like undoing the last edit in a text editor. Let's explore how this works in detail, and why it's such a powerful tool as we move forward. Why do stacks matter so much in programming? They pop up, pun intended, in all sorts of places. Think about a web browser's back button. Each page you visit is pushed onto a stack, and hitting back pops the most recent page off. In coding, stacks are critical for managing function calls. When a function calls another, the current state is pushed, and when it finishes, it's popped to return to the previous state. Another cool use is checking if parentheses in code are balanced, which we'll dive into later. The LIFO nature ensures a natural flow for these tasks, making stacks a go-to choice for managing data where order of removal is key. We'll use Jupyter Notebook to bring this to life interactively, so let's get our hands dirty with some coding and see how it all fits together. Let's create a basic stack using a Python list in a new Jupyter cell. Type stack equals open and close square brackets and run it to initialize an empty stack. Now let's push some elements. Use stack.append1 to add 1 to the top. Since append adds to the end of the list, it becomes our top. Run print stack and you'll see 1. Let's add more. Stack.append2 and stack.append3. Then print again. Output is 1, 2, 3, with 3 now at the top. The append method is perfect here because it always places the new item at the end, aligning with the LIFO idea of pushing to the top. To pop, use stack.pop. This removes and returns the top element, 3, and printing stack now shows 1, 2. This simple approach uses Python's built-in list methods. But let's think about why pop works this way and how it fits the stack concept as we build on it. Let's take it a step further and create a custom stack class for more control and clarity. In a new Jupyter cell, type this code. Class stack, def init self equals int a list of empty lists to hold stack items. Def push self equals append item, adds the new item to the top, end of list. Print exclamation mark if you end up putting push. Equals pop item in stack, return self items pop, removes and returns the top item. Else print stack is empty, cannot pop. Return none. Def is empty, returns len self items equals 0. Def peek, if not self is empty, return self items 1. Returns the top item without removing it. Return none. Now create it with myStack equals stack and test. MyStack push 10, MyStack push 20. Print f popped, MyStack pop. Print top item MyStack peek. Running this gives output like push 10 to the stack, push 20 to the stack, popped 20, and top item 10. The push method adds to the end, pop removes from the end, and peek lets us see the top without changing the stack. This class gives us a structured way to manage a stack, and the print statements help track what's happening. Let's see how this can be applied in a real scenario. Let's dive into a detailed use case, checking if parentheses in an expression are balanced. This is a classic problem where a stack shines. In a new cell, add this code. Def is balanced expression. S is stack. Creates a new stack instance for char in expression. Loops through each character. If char equals where. If it's an opening parenthesis, s.push char. Push it onto the stack. Print pushed s. Stack now its items. If char equals parenthesis, if s is empty. Check if stack is empty. No matching opening. Print found closing without matching s. Unbalanced. Return false. Popped item is s pop. Got the top item. Print 5 popped item stack now its items. If s is empty, for balance, print all parentheses matched. Expression is balanced. Return true. Else print remaining items in stack. Stack now its items. Expression is unbalanced. Return false. Run it for... It pushes 3 little a's, then pops 3 parentheses matched. Expression is balanced. Output is true. For it pushes 2 unparentheses, but only pops 1, leaving 1a, so remaining items in stack. Expression is unbalanced. This process uses the stack to track opening parentheses and match them with closings. If the stack is empty at the end, the expression is balanced, otherwise it's not. This step-by-step tracking with prints helps us see exactly how the algorithm works, making it clear why stacks are perfect for this task. Let's reflect on its importance. To wrap up, we've thoroughly explored what a stack is with its LIFO principle, implemented it using a list and a custom class, with detailed methods like push, pop, isEmpty, and peek, and applied it to the practical problem of balancing parentheses. We saw how append and pop handle the top of the stack, and the parenthesis checker showed how stacks manage nested structures by keeping track of openings until closings arrive. This depth of understanding sets us up beautifully for the next topic, queues, where we'll see a different flow of data. The interactive Jupyter environment helped us visualize each step, and I hope this detailed dive cleared up any confusion. Let's gear up for more. That's it for Part 3, Code Pilots. You've mastered stacks and their real-world magic. Like this video, subscribe for more, and practice with the stack class and the balancer code. Try it with different expressions. Next time, we'll tackle queues, so stay tuned, keep coding, and see you in the next one. Yo, Code Pilots. Welcome to Part 4 of the Python Masterclass, Data Structures. We've mastered arrays and stacks, and now we're moving to queues. If you're new, check the playlist link for Python Basics and OOP. Let's dive into this queue of knowledge with full energy. Let's explore what a queue is. A queue is a linear data structure that follows the FIFO principle, first in, first out. Imagine standing in line at a store. The first person who joins is the first to be served. In a queue, we add elements to the rear with enqueue and remove them from the front with dequeue. This orderly flow is perfect for scenarios where tasks must be handled in the order they arrive, like processing customer requests or managing print jobs. Unlike stacks, which use LIFO, queues ensure fairness by prioritizing the earliest entry. We'll implement this in Python using Jupyter Notebook, breaking down each step to see how this structure organizes data effectively. Let's get started. Why are queues so essential in programming? They're everywhere. In operating systems, queues manage processes waiting for CPU time, ensuring each gets a turn. In web development, they handle incoming requests to prevent server overload, processing them in order, which is crucial for systems where timing matters. We'll use Jupyter's interactive environment to code this up, making it easy to see how queues handle data flow. Let's move to the practical side and build one. Let's create a basic queue using a Python list in a new Jupyter cell. Type queue equals empty brackets and run it to start with an empty queue. Now use queue.append 1 to enqueue 1. This adds it to the rear, making it the first in our FIFO sequence. Run print, open quotes, after enqueuing 1, close quotes, comma, space, queue, close parenthesis, and you'll see open square bracket 1, close square bracket. Let's add more, queue.append 2 and queue.append 3. Then print again. Output is open square bracket 1, 2, 3, close square bracket with 1 at the front and 3 at the rear. To D2, use queue.pop 0 to remove the front element 1 and print queue. Now it's open 2, 3. The append method adds to the rear, and pop 0 removes from the front. But note that pop 0 shifts all elements, which can be slow for large queues. Let's dive deeper into this and improve it. Let's build a custom queue class to give us more control. In a new cell, type class queue, define init self. Remember, self items is an empty list for queue items. Define enqueue self item. Self items append into the rear. Print enqueued item current queue. Print dequeue if not empty isn't empty. Return self items pop 0. Removes and returns the front item. Else left not experience. Print error queue is empty cannot dequeue. Return none. Def is empty self. Return len self items equals 0, returns true if no items. Return len self items, returns the number of items. Create it with myQ equals Q and test. myQ and Q10, myQ and Q20. Print f dq'd myQ dq dq. Output shows nq'd 10, nq'd 20, and dq'd 10. Here nq uses append to add to the rear, and dq uses pop 0 for the front. However, pop 0 has O(n) complexity because it shifts elements, which can be inefficient for big queues. For better performance, we could use collections.dq later, but this gives us a solid base. Let's test it with a real example. Let's simulate a print job queue as a practical use case. In a new cell, add def print jobs jobs. Print q equals q. Print q and quote nq. While not print q is empty. Current job is dq. Print processing job. doc1. doc2. doc3 pf. Print jobs jobs list. Run it. Output shows each job nq'd and dq'd in order, like a printer handling files. Added job doc1 PDF, added job doc2 PDF, added job doc3 PDF, then processing job doc1 PDF, and so on. This FIFO flow ensures jobs are processed fairly, mimicking a real printer queue. The while loop keeps dequeuing until the queue is empty, a common pattern in task management. This example shows how queues maintain order, which is vital in systems like print servers or task schedulers. Let's reflect on its significance. To wrap up, we've deeply explored what a queue is with its FIFO principle, implemented it using a list and a custom class with nq, dq, isEmpty, and size, and applied it to a print job simulation. We learned how append adds to the rear and pop 0 removes from the front, noting the efficiency trade-off with large data. Queues are key for managing tasks sequentially, from operating systems to everyday apps. And this hands-on approach in Jupyter helped us see every step. This prepares us for linked lists next, where we'll see a different way to handle data. Let's get excited for that. That's it for Part 4 Code Pilots. You've conquered queues and their applications. Like this video, subscribe for more, and practice with the queue class and print job code. Try it with your own job list. Next time, we'll dive into linked lists, so stay tuned, keep coding, and see you in the next one. Yo, Code Pilots! Welcome to Part 5 of the Python Masterclass, Data Structures. We've tackled arrays, stacks, and queues, and now it's time for linked lists. If you're new, check the playlist for Python Basics and OOP. Let's dive into this linked adventure. Let's start with what a linked list is. Unlike arrays with their fixed or contiguous memory, a linked list is a dynamic data structure where each element, called a node, contains data and a reference, or link, to the next node. This forms a chain where nodes are connected, not stored in one block. There are types like singly linked, one-way links, and doubly linked, two-way links, but we'll focus on singly linked for now. The beauty is flexibility. Adding or removing nodes doesn't require shifting elements like arrays, just updating links. We'll build this in Python using Jupyter Notebook, exploring how it differs from previous structures. Let's get into the details. Why are linked lists important? They shine where data changes a lot. Imagine a playlist. Adding a song or skipping one is easy with a linked list because you just adjust the links, not the whole array. They're used in applications like undo, redo stacks in software, managing browser history, or even in operating systems for task scheduling. Unlike arrays, they don't need contiguous memory, making them great for systems with fragmented memory. We'll code this up interactively, seeing how nodes link together, so let's move to the implementation and understand its flow. Let's create a basic linked list. In a new Jupyter cell, define a node class. Class node, def init method, self data, stores the data. Now, stores the data, self next equals none, points to the next node. Now the linked list class, class linked list, def init method, self head equals none, start with an empty list. Def append self data, new node is node data. If not self head is new node. Else, current self head, while current next. Current equals current.next. Current.next equals new node. Test it. LL equals linked list. LL append 1, LL append 2, print, linked list created. This sets up a list with nodes 1 and 2, where each node links to the next. The append method adds nodes to the end by traversing the list. Let's see how this linking works and why it's different from array indexing. Let's add methods to traverse and display. Update the linked list class. Def display, self, elements equals elements. Current equals self head, while current. Elements append current data. Current equals current next. Print, linked list, elements. Test it. LL display. Output is 1, 2. This traverses from head, collecting data, until next is none. Now, add a delete method. Def delete self. Data. If not self head, print. List is empty. Return if self head data equals data. Self head is equal to head.next. Return. Current is self head, while current.next and current.next.data equal data. Current.next. If current.next is current.next, print deleted data. Else print not found. Test. LL append 3, LL display, output shows 1, 2, 3, then 1, 3 after deleting 2. This shows how links are updated. Let's explore its flexibility. Let's try a use case. Managing a dynamic task list. Add def manage tasks. Task list equals linked list. For task and tasks, task list append task. Print f added task list display. Task list delete tasks 1. After removing second task list display. Tasks equals email, meeting, call. Manage tasks. Run it, output adds email, meeting, call, displays email, meeting, call, deletes meeting, and shows email call. This mimics a to-do list where tasks can be added or removed dynamically, leveraging linked list's strength in handling changes. Let's analyze its benefits. To wrap up, we've learned what a linked list is with its node-based structure, implemented it with a node and linked list class, including append, display, and delete, and applied it to a task management use case. Unlike arrays, it uses pointers for flexibility, though traversal is slower over n. This dynamic nature makes it ideal for acts needing frequent insertions or deletions. Jupyter helped us see each step, setting us up for trees next. Let's get ready. That's it for Part 5, Code Pilots. You've mastered linked lists. Like this, subscribe, and practice with the linked list class. Try adding more methods. Next time, we'll explore trees, So stay tuned, keep coding, and see you soon. Yo, Code Pilots! Welcome to Part 6 of the Python Masterclass, Data Structures. We've covered linked lists, and now we're branching into trees. If you're new, check the playlist for Python basics and previous topics. Let's grow this knowledge tree together. Let's dig into what a tree is. A tree is a nonlinear data structure that organizes data hierarchically, like a family tree or a company org chart. It has a root node at the top with child nodes branching out, and each node can have 0 or more children. Key terms include parent, child, leaf, nodes with no children, and height, levels of the tree. Unlike linear structures like lists, trees model relationships, making them great for hierarchical data. We'll focus on a binary tree where each node has at most 2 children, left and right. We'll build this in Jupyter Notebook, exploring how it differs from flat structures. Let's plant the seeds. Why are trees so powerful? They're used everywhere. In file systems, trees organize directories and files with the root at the top. In databases, they speed up searches with structures like B-trees. Decision trees in AI help classify data by branching decisions, like predicting weather. Their hierarchical nature allows efficient traversal and searching, though balancing is key for performance. We'll code a basic binary tree, seeing how nodes connect vertically, so let's move to the implementation and understand its structure. Let's create a binary tree. In a new Jupyter cell, define a node class. Class node, def initself, data. Self data equals data. Stores the data. Self left is none, left child. Self right is none, right child. Now a simple tree class. Class binary tree, def initself. Self root equals none. Start with no root. Def insert self data. If not self root equals node data. Else self insert recursive, self root data. Def insert recursive, self node data. If data less than node data, if node left is none, node left equals node data. Else self insert recursive, node left data. Else if node right is none, node right equals node data. Else self insert recursive, node right data. Test it. Tree equals binary tree. Tree insert 5, tree insert 3, tree insert 7, print, tree created. This builds a tree with 5 as root, 3 as left, and 7 as right. Let's see how it grows. Let's add a traversal method. Update the binary tree class. Def inorder traversal. Result is equal to 0. Self inorder recursive result. Return result def inorder recursive. Node result. If node self inorder recursive. Node left result. Result append node data. Self inorder recursive. Node right result. Test it. Print inorder traversal. Tree dot inorder traversal. Output is 3, 5, 7, showing left, root, right order. This visits nodes systematically. Useful for sorting. Let's add a search method. Def search self data. Return self underscore search recursive self root data. Def underscore search recursive node. If node is none or node data equals data, return node. If data less than node data, return self underscore recursive node left data. Return self underscore recursive node right data. Test. Print search for 3. Dot tree search 3. Returns the node with 3. This shows tree navigation. Let's apply it. Let's use a tree for a file system simulation. Add def simulate file system. fstree equals binary tree. Files 10, 5, 15, 3. Simulating file sizes or IDs for file and files. fstree insert file print. File system tree in order. fstree in order traversal. Search result equals fstree search 7. Print found file 7. Yes. If search result else no. Simulate file system. Run it. Output shows 3, 5, 7, 10, 15. And found file 7. Yes. This mimics organizing files hierarchically with search for quick access. Let's analyze its use. To wrap up, we've explored what a tree is with its hierarchical structure. Implemented a binary tree with node and binary tree classes, including insert, in-order traversal, and search, and applied it to a file system. Trees offer efficient organization and searching, though balancing is needed for optimal performance. Jupyter's interactivity helped us see each step, setting us up for graphs next. Let's prepare. That's it for part 6. Code pilots, you've mastered trees. Like this, subscribe, and practice with the binary tree class. Try adding more nodes. Next time, we'll tackle graphs, so stay tuned. Keep coding, and see you soon. Yo, code pilots! Welcome to part 7 of the Python Masterclass, Data Structures. We've journeyed through trees, mastering their hierarchical beauty, and now we're stepping into the interconnected world of graphs. If you're new to this series, don't worry. Check the playlist, link for the basics, and catch up on previous topics like trees and arrays. Graphs are all about relationships, and today we're going to weave a network of knowledge together. So, grab your coding gear and let's dive in. Let's start by unpacking what a graph really is. At its core, a graph is a non-linear data structure that models relationships between pairs of objects, which we call nodes or vertices, connected by edges. Think of it like a social network where people are nodes and friendships are the edges linking them. Unlike trees, which have a single root and a strict parent-child hierarchy, graphs can have cycles, meaning you can loop back to where you started, or multiple paths between nodes. They come in two main flavors: directed, where edges have a direction, like a one-way street, and undirected, where connections go both ways, like a two-way road. Plus, edges can be weighted, carrying values like distances, or unweighted, just showing presence. This flexibility makes graphs incredibly powerful for representing complex systems, from roadmaps to the internet. We'll focus on building an undirected graph in Jupyter Notebook, exploring how these nodes and edges come together. Let's get our hands dirty. Why should we care about graphs? They're the unsung heroes behind many systems we use daily. Imagine social media platforms like X. Graphs track who follows whom, building a web of connections that power friend suggestions. In GPS apps, graphs map out routes between cities with edge weights representing distances or travel times, helping you find the fastest path. Even in cutting-edge AI, graphs drive recommendation engines, linking your preferences to similar users to suggest movies or products. What sets graphs apart is their ability to handle cyclic and multipath relationships. Unlike the linear or tree-like structures we've seen before, we'll dive into coding a basic graph, focusing on how to add and traverse these connections. So let's set up our workspace and start building. Let's create a graph from scratch. We begin with a graph class, using a dictionary to store our nodes and their connections. Think of it as a lookup table where each key is a node and the value is a list of its neighbors. We initialize this dictionary as empty to start fresh. Now, to add an edge between two nodes, we need a method that checks if each node exists. If not, it creates an empty list for that node. Then, it connects both nodes to each other to make it undirected, ensuring symmetry in the relationship. For example, adding an edge between node 0 and node 1 means 0 points to 1 and 1 points to 0. Let's test this by adding edges, first between 0 and 1, then 1 and 2. After running the code, we get node 0 is connected to 1, node 1 is connected to 0 and 2, node 2 is connected to 1. This output confirms our network is forming. Each node now knows its neighbors, and we can see the structure taking shape. Let's explore this further by adding more logic. Next, let's enhance our graph with a display method and a depth-first search, DFS, to navigate it. The display method is straightforward. It loops through each node in our dictionary and prints its list of connected nodes, giving us a clear picture of the graph. For DFS, we're building a tool to check if a path exists between two nodes. We start with a set to track visited nodes. Add the starting node and check if it's our target. If not, we recursively explore each unvisited neighbor, diving deeper until we find the target or exhaust all options, then return true or false. This is like exploring a maze, step by step. Let's test DFS from node 0 to node 2 on our current graph. After running it, we get path from 0 to 2, true. This tells us there's a valid path, 0 to 1, then 1 to 2, proving our search works. Let's break down how this recursion handles the flow and why it's so efficient for connected networks. Let's take this a step further and simulate a social network to see graphs in action. We'll define a function that creates a graph and adds a list of connections, forming a cycle, like a group of friends where everyone is linked. For each pair, we call our addEdge method to build the network. Then we display the connections to visualize it, and use DFS to confirm paths between nodes. Let's test it with a cycle, 0, 1, 1, 2, 2, 3, 3, 0. After running the code, the output is node 0 is connected to 1, 3. Node 1 is connected to 0, 2. Node 2 is connected to 1, 3. Node 3 is connected to 2, 0. And is there a path from 0 to 3? True. This cycle mimics a close-knit community where you can reach anyone through the network. Let's dive deeper. Imagine adding weights to these edges for friendship strength or distance, and how that could change our path-finding strategy. This real-world application shows graphs' versatility. To wrap up this awesome ride through graphs, we've delved into what a graph is, exploring its node-edge relationships and the differences from trees, like handling cycles and multiple paths. We implemented a basic undirected graph by setting up a dictionary to store connections, added a display method to visualize the structure, and crafted a DFS to navigate and find paths efficiently. We then applied this to a social network simulation, seeing how cycles and connectivity work in practice. Graphs are foundational for routing algorithms, network analysis, and even game design, where paths between locations matter. Jupyter's interactive environment let us build and test each piece step by step, giving us confidence to tackle more complex structures. Let's reflect on how this opens doors to advanced topics. Pretty exciting, right? But before we sign off, let's think about expanding this further. What if we added weights to our edges to represent costs, like time or effort? We could modify DFS to find the shortest path, or even switch to a breadth-first search for a different approach. Imagine a game map where players move between locations. Graphs could optimize their routes. We'll explore these ideas in future episodes. But for now, practice with this graph. Try adding more nodes or testing different paths. Jupyter's here to help you experiment, so don't hesitate to play around. That's it for Part 7, Code Pilots. You've mastered the art of graphs, from theory to hands-on coding and real-world use. Like this video, hit that subscribe button, and drop a comment if you've got questions or ideas for the next topic. The journey's just heating up. Next time, we'll pile into heaps. So stay tuned, keep coding, and I'll see you in the next adventure. Yo, Code Pilots! Welcome to Part 8 of the Python Masterclass Data Structures. We've navigated graphs and their web of connections, and now we're stacking up with heaps, a structure that's all about order and efficiency. If you're new here, no sweat. Check the playlist for the basics and earlier topics like trees and graphs. Heaps are like the VIP line at a club, prioritizing the most important elements first. So, buckle up, grab your code editor, and let's pile into this adventure. Let's break down what a heap is. A heap is a specialized tree-based data structure that follows the heap property. In a min heap, every parent node is less than or equal to its children, ensuring the smallest value sits at the root. While in a max heap, the parent is greater than or equal, keeping the largest at the top. This creates a partially ordered structure, not a full binary search tree, which makes heaps perfect for quick access to extremes. They're typically visualized as binary trees, but we'll implement them using a list for simplicity, leveraging array indices to manage the tree-like behavior. Heaps are dynamic. After adding or removing elements, they adjust to maintain this property, making them ideal for priority-based tasks. We'll build a min heap in Jupyter Notebook, diving into how this order is maintained. Let's get started. Why are heaps a big deal? They're the secret sauce behind many optimized systems. Think of a hospital emergency room. Heaps power priority queues, where the most critical patients are treated first based on severity. In algorithms, heaps enable heap sort, a comparison-based sorting technique, or help find the kth smallest element efficiently. Even operating systems use heaps to manage process scheduling, prioritizing tasks by urgency. Their standout feature is O1, access to the root, the min or max value, and O log n adjustments, balancing speed and structure. We'll code a min heap today, focusing on insertion and removal. So let's roll up our sleeves and start coding. Let's build our min heap. We start with a heap class, using a list to store elements. Think of it as a flat representation of a binary tree, where the parent-child relationship is calculated with indices. We initialize an empty list to begin. For insertion, we append a new value to the end and shift it up to maintain the min heap property, comparing it with its parent at index I-1 over 2, and swapping if it's smaller, moving up until it's in place. Let's test this by adding 5, then 3. After running the code, we get heap 3, 5. This shows 3 bubbled up to the root. Since it's smaller, our heap is ordering itself. Let's dig into how these swaps work and why the index math keeps the tree balanced. Now let's add methods to remove the minimum and display the heap. Removal starts by taking the root, the smallest value, replacing it with the last element, and shifting it down to restore the heap property. We compare it with its children at 2i plus 1 and 2i plus 2, and swap with the smallest child if needed, moving down until it fits. The display method simply prints the list for a quick look. Let's test this on 3, 5, 7. After removing the minimum, we get removed min 3 and heap 5, 7. Then, displaying again shows heap 5, 7. The structure adjusted by moving 5 down. Let's break down this sift down process. How does it ensure the smallest value always rises, and what happens if we add more elements? Let's apply this to a priority task scheduler, a real-world use case. We'll create a function that builds a heap and adds tasks with priorities, where lower numbers mean higher urgency. We insert each task, then process them by removing the minimum one by one until the heap is empty. Let's test it with tasks 5, 2, 8, 1. After adding them, the display shows heap. Processing task with priority 2. Processing task with priority 3. Processing task with priority 5. Processing task with priority 8. This mimics a system where urgent tasks, like fixing a server crash, get handled first. Let's explore how adding more tasks or changing priorities could scale this up. To wrap up this epic dive into heaps, we've uncovered what a heap is, mastering its order-maintaining property, and how it differs from trees or graphs with its focus on extremes. We implemented a min heap using a list, adding insertion and removal logic with sift up and sift down techniques, and visualized it with a display method. We then applied it to a task scheduler, seeing how priority ordering works in action. Heaps are crucial for algorithms like Dijkstra's shortest path or real-time systems needing quick prioritization. Jupyter's step-by-step testing helped us nail each part, setting us up for even cooler challenges ahead. How pumped are you for that? Before we wrap, let's brainstorm some next steps. What if we added max heap support to handle descending order? Or implemented a heap-based median finder for streaming data? Picture a game where players queue for power-ups. Heaps could manage turn order by strength. We'll tackle these in future episodes, but for now, practice with this code. Try inserting a bunch of numbers or building a custom scheduler. Jupyter's your playground, so experiment and see what happens. That's it for Part 8, Code Pilots. You've conquered heaps, from theory to practical coding and beyond. Like this video, smash that subscribe button, and drop a comment with your thoughts or next topic ideas. The adventure's heating up. Next time, we'll explore even wilder data structures. So stay tuned, keep coding, and catch you in the next one. Yo, Code Pilots, welcome to Part 9 of the Python Masterclass, Data Structures. We've conquered heaps and their ordered stacks, and now we're branching into tries, a structure built for strings and super fast lookups. If you're new to the crew, no problem. Hit the playlist for the basics and catch up on graphs and heaps. Tries are like a dictionary on steroids, organizing words for autocomplete or searches. So grab your coding hats and let's dive into this wordy adventure with some deep dive explanations. Let's unpack what a trie is. A trie, short for retrieval tree, is a tree-like data structure designed to store a dynamic set of strings, where each node represents a character and paths from the root to a leaf spell out complete words. Unlike binary trees or heaps, tries are all about prefix-based storage. Every edge is labeled with a character, and the structure lets us share common prefixes efficiently. For example, words like cat and car share the C and A nodes, splitting at T or R. Each node can mark if it's the end of a word, making tries perfect for tasks like autocomplete or spell checking. We'll build a basic try in Jupyter Notebook, exploring how it organizes strings step by step. Let's get cracking. Why are tries so cool? They're the backbone of many text-based tools. Think of Google's autocomplete. Tries suggest words as you type by quickly finding all prefixes. Spell checkers use them to flag misspelled words by checking against a dictionary stored in a try. Even in networking, tries help route IP addresses by matching prefixes efficiently. Their magic lies in O of M time for operations like insertion or search, where M is the string length, beating hash tables for prefix queries. We'll code a try today, focusing on adding words and searching. With a detailed breakdown of every line, let's set up and start building. Let's construct our try. We start with a try class, using a nested dictionary, where each node holds a dictionary of children and a flag for word endings. We initialize the root as an empty dictionary, with self.root equals empty dictionary. This is our starting point, a blank slate for all characters. The self.end underscore symbol equals star is a special marker to show when a word ends, described as star for clarity. Now, let's dive into the insert method. First, current equals self.root sets our starting node. Then, for each char in word, we check if char not in current. If the character isn't there, we create a new empty dictionary with current char equals empty dictionary. Next, current equals current char moves us to that new node. Finally, current self.end underscore symbol equals true marks the end of the word. Let's test this by adding cat and car. After running, we print the structure. Root has C pointing to a node with A, which splits to T end and R end. Let's break down each line to see how this builds the try. Now, let's add the search method. We start with current equals self.root to begin at the root. For each char in word, we check if char not in current. If it's missing, return false since the word can't exist. If it's there, current equals current char moves to the next node. At the end, return self.end underscore symbol in current checks if the word is complete. Let's test with cat. It follows C to A to T and sees the end marker, so it's true. Next, the prefix underscore search method starts with current equals self.root. For each char in prefix, it checks if char not in current and returns an empty list if missing, or moves with current equals current char. Then, results equals empty list initializes a list, and self._collect underscore words, current prefix results, gathers all words. The underscore collect underscore words helper checks if self.end underscore symbol in node to add the prefix if it's a word, and for each char in node, if char not equals self.end underscore symbol. It recurses with self._collect underscore words, node char, prefix plus char results. Testing CA gives cat and car. Let's explore each line's role in this recursion. Let's apply this to an autocomplete system. We define autocomplete prefix words where try equals try creates a new try. For each word in words, try.insertWord adds it, and print fstring added word : end fstring word shows progress. Then try.display visualizes the structure. Finally, suggestions equals try.prefix underscore search prefix gets options, and print fstring autocomplete for single quote prefix single quote : end f-string suggestions displays them. Testing with cat, car, dog, catnip, and caw shows added word cat, added word car, etc. Then autocomplete for CA, cat, car, catnip. Let's break down how each line builds and queries the try for this practical use. Imagine scaling it with thousands of words. To wrap up this deep dive into tries, we've learned what a try is, mastering its prefix-based organization, and how it differs from trees or heaps with its string focus. We implemented a try using nested dictionaries, explaining every line of insert, search, and prefix_search, and visualized it with a display method. We applied it to an autocomplete system, seeing how it powers text predictions step by step. Tries shine in applications like IP routing or dictionary lookups, and Jupyter's testing helped us perfect each part. This sets us up for wilder structures. How excited are you for the next challenge? Before we sign off, let's think ahead. What if we added deletion to remove words, or built a compressed try for huge data sets? Imagine a word game. Tries could validate moves instantly. We'll tackle these in future episodes, but for now, practice. Try a big word list or test prefixes. Jupyter's your lab, so experiment freely. That's it for Part 9, Code Pilots. You've mastered tries with line-by-line insights from theory to coding and beyond. Like this video, smash that subscribe button, and comment with your thoughts or topic ideas. The journey's getting epic. Next time, we'll explore more data structures. So stay tuned, keep coding, and catch you next time. Yo, Code Pilots! Welcome to Part 10 of the Python Masterclass, Data Structures. We've tamed tries and their string magic, and now we're leveling up with segment trees, powerful tools for range queries. If you're new to the squad, no worries. Check the playlist for the basics and catch up on heaps and tries. Segment trees are like supercharged arrays, making range operations lightning fast. Grab your coding gear and let's dive into this query-filled adventure with detailed breakdowns. Let's break down what a segment tree is. A segment tree is a binary tree designed to store information about intervals or segments of an array, letting us perform range queries like sum or minimum efficiently. Each node represents a range, and the tree splits it into smaller segments, pre-computing results for quick access. For example, for an array of numbers, a segment tree can find the sum of any range in log n time, way faster than scanning the array. We'll build one in Jupyter Notebook, exploring how it handles range operations step by step. Let's get started. Why are segment trees awesome? They're key in competitive programming and real-world apps. Think of finding the minimum temperature over a week's data, or summing sales in a store over days. Segment trees handle these in a flash. They shine in scenarios needing frequent range updates or queries, like financial data analysis or game physics. With O of log n time for queries and updates, they beat linear scans hands down. We'll code a segment tree today, focusing on building it and querying sums. With a line-by-line deep dive, let's set up and build. Let's construct our segment tree. We start with a segment tree class, using an array to store the tree where each node holds a range's sum. We initialize with self.tree equals a list of zeros with size 4 times the input array length. This ensures space for all nodes. The self.build method takes the array and indices low and high. First, current equals self.tree sets the tree array. Then, if low equals high, current index equals array low sets the leaf value. Else, we find mid equals low plus high divided by 2. Build the left child with self.build array low mid, and the right child with self.build array mid plus 1 high. Finally, current index equals current left child index plus current right child index computes the sum. Let's test this with an array like 1, 2, 3, 4. After building, we'll see how nodes store range sums. Let's break down each line to understand this construction. Now, let's add the query method. We define query with start and end indices. First, current equals self.tree accesses the tree. The helper method, query underscore helper, takes node index, node start, node end, and query range, start end. If node start greater than end or node end less than start, return 0 for no overlap. If node start greater than or equal start and node end less than or equal end, return current node index for full overlap. Else, find mid equals node start plus node end divided by 2, and return query underscore helper left child plus query underscore helper right child. Testing with range 1 to 3 on our array should give sum 6. Let's explore each line's role in this recursive query. Let's apply this to a practical example. Tracking running sums. We define update to modify a value, then query ranges. The update method takes index and value, setting array index to value, and rebuilding with self.build array 0 length -1. For query, we test ranges like 0 to 2 or 1 to 3. With array 1, 2, 3, 4, updating index 1 to 5 gives a new sum. Running queries shows updated ranges. Let's break down how each line updates and queries the tree, imagining a live data stream. To wrap up this deep dive into segment trees, we've learned what a segment tree is, mastering its ability to handle range queries efficiently compared to arrays. We implemented a segment tree using an array, explaining every line of build, query, and update, and tested it with practical sums. We applied it to a running sum tracker, seeing how it adapts to changes step by step. Segment trees excel in competitive coding or real-time analytics, and Jupyter's testing helped us nail each part. This sets us up for even crazier structures. How pumped are you for what's next? Before we sign off, let's think ahead. What if we added lazy propagation for range updates, or used it for minimum range queries? Picture a game tracking player scores. Segment trees could optimize it. We'll dive into these in future episodes, but for now, practice. Try a larger array or different queries. Jupyter's your playground, so experiment away. That's it for Part 10, Code Pilots. You've mastered segment trees with line-by-line insights. From theory to coding and beyond. Like this video, smash that subscribe button, and drop a comment with your ideas or next topic wishes. The journey's getting wilder. Next time, we'll tackle more data structures. So stay tuned, keep coding, and catch you later. Yo, Code Pilots! Welcome to Part 1 of the Python Machine Learning course, where we're stepping into the exciting world of machine learning. We're starting with NumPy, the backbone of numerical computing in Python. If you're new to the crew, no problem. This is the beginning, so you're right on time. NumPy powers data manipulation for ML, so grab your coding tools and let's explore this game changer with detailed breakdowns. Let's unpack what NumPy is. NumPy, short for Numerical Python, is a library that provides support for large, multi-dimensional arrays and matrices, along with a collection of mathematical functions to operate on them. Unlike Python lists, NumPy arrays are fast and memory efficient, making them perfect for scientific computing and machine learning. For example, you can perform element-wise operations on millions of numbers in one go. We'll set up NumPy in Jupyter Notebook, create our first array, and see how it beats regular lists step by step. Let's get rolling. Why is NumPy a big deal? It's the foundation of almost every ML library, like Pandas, Scikit-learn, and TensorFlow. Think of training a model. NumPy handles the heavy lifting with array operations. Data scientists use it for everything from image processing to statistical analysis, thanks to its speed and flexibility. With optimized C-based code, it beats Python loops by miles. We'll code with NumPy today, focusing on arrays, basic operations, and functions. With a line-by-line deep dive, let's set up and start building. Let's create our first NumPy array. We start by importing NumPy with import NumPy as NP. Then, we create a simple array with np.array passing a list like 1, 2, 3, 4. This gives us a one-dimensional array. We check its type with type and shape with np.shape to see it's a numpy.ndire with length 4. Next, we make a two-dimensional array with np.array passing a list of lists like 1, 2, 3, 4, 5, 6. This is a 2x3 matrix. We access elements with array indexing like array0 or array1, 0, and modify with array0 equals 10. Let's test performance by timing a sum with np.sum versus a Python loop. Let's break down each line to see NumPy's power. Now let's explore array operations. We start with element-wise addition using array plus array, or np.add, on two arrays like 1, 2, and 3, 4. Result is 4, 6. We multiply with array times array, or np.multiply. Try 1, 2 times 2, 3 for 2, 6. We use np.dot for matrix multiplication on two-dimensional arrays. Broadcasting lets us add a scalar, like 2, to array 1, 2, 3. Result is 3, 4, 5. We apply functions like np.sin on array 0, 1, 2 for sign values. Testing with a larger array shows speed. Let's dive into each line's role in these operations. Let's apply NumPy to a practical example, data analysis. We create a sample dataset with np.array for temperatures like 22, 23, 21. We compute mean with np.mean, max with np.max, and min with np.min. Let's say mean is 22. We filter values above 22 with array greater than 22. Then we generate random data with np.random.rand for a 3x3 matrix and analyze it. Update in a value and recalculate and shows NumPy's flexibility. Let's break down how each line processes this data step by step. To wrap up this deep dive into NumPy, we've learned what NumPy is, mastering its array-based power for numerical tasks in machine learning. We implemented arrays, explored operations like addition and multiplication, and applied it to data analysis with functions like mean and random. NumPy's speed and tools make it indispensable for ML workflows, and Jupyter's testing helped us nail each part. This sets us up for deeper ML topics. How excited are you for what's next? Before we sign off, let's think ahead. What if we combined NumPy with Pandas for data frames, or used it for matrix operations in neural networks? Imagine analyzing real data sets. NumPy's your starting point. We'll cover these in future episodes, but for now, practice. Try creating arrays or timing operations. Jupyter's your lab, so experiment freely. That's it for Part 1, Code Pilots. You've mastered NumPy with line-by-line insights, from basics to applications. Like this video? Smash that subscribe button and comment with your thoughts or ML topic ideas. The journey's getting exciting. Next time, we'll dive deeper into machine learning, so stay tuned. Keep coding, and catch you later. Hey there, Code Pilots. Welcome to Part 2 of the Python Machine Learning course, where we're taking NumPy to new heights with advanced array operations. In our last session, we laid the foundation with basic arrays and simple operations. Now, we're diving into the world of multidimensional matrices, broadcasting techniques, and performance optimization, all essential for machine learning workflows. Whether you're joining us fresh or continuing from Part 1, this is your chance to level up. Grab your coding setup, open Jupyter Notebook, and let's explore these advanced concepts together with hands-on examples and thorough explanations. Let's begin by unpacking what advanced array operations mean for us. We're moving beyond the one-dimensional arrays of Part 1 to multi-dimensional structures. Think 3D arrays for image stacks or 4D arrays for video data, which are staples in fields like computer vision and deep learning. Then there's broadcasting, a clever NumPy feature that lets us perform operations on arrays of different shapes without writing loops, saving both time and memory. We'll also tackle performance optimization to handle large data sets efficiently. To bring this to life, let's set up our Jupyter environment, create a 3D array as our first example, and walk through its structure and properties in detail. Picture a 2x2x3 matrix, and let's build it step by step to see how it works. These advanced techniques are game changers for machine learning because they address real-world data complexities. For instance, a 3D tensor might represent a batch of images fed into a neural network, while a 4D array could hold video frames for motion analysis. Graphics broadcasting simplifies tasks like adding a bias vector to every row of a matrix, eliminating the need for manual loops and boosting speed. Optimization ensures we can process massive data sets, like gigabytes of sensor data, without bogging down our system, making NumPy a go-to tool for data scientists. Today, we'll construct a 3D array, apply broadcasting to reshape operations, and optimize a large array sum, exploring each process with practical code and analyzing the results to understand their impact fully. Let's get our hands dirty by creating a 3D array. We start by importing NumPy with import NumPy as NP, setting the stage for our numerical adventures. Now, let's imagine we're working with a small 3D dataset, like a stack of two 2x3 grids. Think of it as 2 layers of a mini image. We build this with np.array, passing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which forms a 2x2x3 matrix. To verify, we use np.shape, expecting 2, 2, 3, and print the array to see its structure. Next, we access a 2D slice with AR3D 0 to inspect one layer. Then modify a value like AR3D 0, 0, 20 to watch the change ripple through. To showcase NumPy's efficiency, we generate a 100 by 100 by 100 array with np.zeros, time np.sum, and compare it with a nested Python loop. Let's run this, examine the output, and discuss why NumPy's speed is a big deal for large-scale computations. Now, let's dive into broadcasting, a feature that makes NumPy stand out. Consider a 2x3 matrix created with np.array, like 1, 2, 3, 4, 5, 6, and a vector 1, 2. Adding these directly would clash due to shape mismatch, but broadcasting magically extends the vector to 1, 2, 3, 1, 2, 3, then adds it to the matrix, yielding 2, 4, 6, 5, 7, 9. To understand this, we use np.broadcastArrays from numpy.lib.stridetricks to align shapes and print the result, revealing how NumPy handles this internally. We'll also apply np.exp to the matrix, computing the exponential of each element, a common step in neural network activations, and discuss how this scales with larger arrays. Now, let's try another example with a 3x2 matrix and a 1x2 vector to see broadcasting's versatility in action. We create a matrix with np.array like 1, 2, 3, 4, 5, 6, and a vector 1, 2. Adding them, broadcasting stretches the vector to 1, 2, 1, 2, 1, 2, resulting in 2, 4, 4, 6, 6, 8. Let's run this in code. We'll use matrix plus vector, print the output, and use np.broadcastArrays to confirm the shape alignment, which should give us two 3x2 arrays. The output shows each row of the matrix increases by the vector's values, demonstrating how broadcasting adapts to column-wise operations. This flexibility is key for applying the same transformation across multiple rows efficiently. Let's explore this further by testing with a negative vector, like -1, -2, and observing the symmetric decrease. Performance optimization is where NumPy proves its worth with big data. We create a 100 by 100 by 100 array using np.zeros and measure np.sum's execution time, which handles the task in seconds. For contrast, we write a triple-nested Python loop to sum the same array, noting how it takes much longer. Let's time both and compare the results. To add flexibility, we define a custom function with np.vectorize, say doubling positive values while keeping zeros or negatives as is, e.g., -1, 0, 1, 2 becomes 0, 0, 2, 4, and apply it to a sample array. Finally, we simulate a 10 by 10 by 3 image dataset with np.random.rand, 3 color channels, filter values above 0.5 with a Boolean mask, and print a sample to see the effect. Let's run this, check memory usage with np.info, and explore how these optimizations prepare us for real-world ML challenges. As we conclude this deep dive, we've thoroughly explored advanced array operations with multi-dimensional matrices, mastered broadcasting for efficient computations, and optimized performance for large datasets in NumPy. We built and manipulated 3D arrays, experimented with shape alignment and exponential functions, and tested optimizations with practical examples, all while using Jupyter to reinforce our learning. These skills lay a solid foundation for machine learning tasks like image processing or model training, and we've seen how they work in action. How confident do you feel applying these techniques to your own projects now? Looking ahead, imagine using these 3D arrays to process satellite imagery or optimizing a neural network's weight matrices for better predictions. Why not challenge yourself by creating a 4D array in Jupyter or testing broadcasting with mismatched shapes on a sample dataset? Load a CSV file with thousands of rows and time NumPy's operations, Each experiment sharpens your skills. We'll build on this in our next session with more advanced topics. So keep experimenting and let your curiosity guide you. That wraps up Part 2, Code Pilots. You've gained a comprehensive grasp of NumPy's advanced features with detailed examples and insights. If this journey excited you, smash that like button, subscribe for more, and share your thoughts or ML ideas in the comments. We're just getting started. Stay tuned. Keep coding. Hey there, Code Pilots. Welcome to Part 3 of the Python Machine Learning course, where we're putting NumPy into action with practical applications. In Parts 1 and 2, we mastered the basics and advanced operations. Now, it's time to apply those skills to real-world scenarios. We'll tackle data analysis, generate random numbers, and build a mini project to solidify your understanding. Whether you're joining fresh or continuing the journey, this is where theory meets practice. Fire up your Jupyter notebook, and let's dive into these hands-on examples with detailed guidance. Let's start by exploring what practical applications mean for NumPy. We'll use its powerful tools to analyze datasets, like calculating statistics or filtering data, tasks common in machine learning prep work. We'll also dive into random number generation, essential for simulations and model testing, and wrap up with a mini project to tie it all together, such as a simple data predictor. These skills are the bridge between learning and building real ML systems. To get going, let's set up our Jupyter environment, load a sample dataset, and walk through each step with clear examples. Imagine analyzing temperature data, and let's make it happen step by step. Why are these applications so important? In machine learning, data analysis with NumPy helps us understand datasets before training models. Think computing means or spotting outliers. Random number generation is critical for creating synthetic data or initializing neural network weights, ensuring robust testing. A mini project, like predicting a trend, gives you a taste of end-to-end workflows. These tools empower data scientists to handle everything from weather forecasting to financial modeling. Today, we'll analyze a dataset, generate random arrays, and build a basic predictor, exploring each line of code with practical examples and discussing its real-world relevance in depth. Let's begin with data analysis using a sample dataset. We start by importing NumPy with the line import NumPy as NP, which brings in the library and lets us use it with the shorthand NP. This is our foundation for all numerical work. Next, we create a temperature dataset with temperatures equals np.array 22, 23, 21, 25, 24. Turning a Python list into a NumPy array for efficient operations. We print it with print temperatures to see the values. Then we compute the mean with print mean np.mean temperatures, which calculates the average. Let's expect around 23. We find the maximum with print max np.max temperatures, and minimum with print min np.min temperatures to get the range. To filter, we use print above 23 temperatures greater than 23. To extract warmer days, showing how Boolean indexing works. Finally, we calculate the standard deviation with print standard deviation np.std temperatures to measure variability. For a bigger challenge, we simulate 100 random temperatures with random temps equals np.random.normal 23 to 100, where 23 is the mean, 2 is the standard deviation, and 100 is the sample size. We print the mean and standard deviation with print random temperatures mean, np.mean random temps, and print random temperatures sd, np.std random temps to analyze the distribution. Let's run this, inspect each output, and discuss what these stats reveal about our data. Next, let's explore random number generation, a cornerstone for simulations. We start with np.random.rand33 to create a 3x3 matrix of uniform random numbers between 0 and 1, ideal for algorithm testing, and print it with print 3x3 uniform random matrix random matrix. For a normal distribution, we use np.random.normal 0, 1, 4, 4 with a mean of 0, standard deviation of 1, and a 4x4 shape, printing it with print 4x4 normal random matrix, normal matrix. To ensure reproducibility, we set a seed with np.random.seed42, which fixes the random sequence. Then regenerate a 3x3 matrix with np.random.normal 0, 1, 3, 3 and print it with print reproducible 3x3 matrix, repro matrix, to confirm consistency. For a practical twist, we simulate image noise with noise grid equals np.random.rand 10, 10, a 10x10 grid, and filter values above 0.7 with filter mask equals noise grid greater than 0.7, printing the shape with print filtered noise shape, filter mask dot shape, and a sample with print sample filtered noise, nen noise grid filter mask. Let's execute each line, review the outputs, and discuss how random data supports tasks like Monte Carlo simulations or neural network initialization. Now, let's build a mini project, a simple trend predictor. We start with sales equals np.array 100, 105, 110, 115, 120, a time series of weekly sales, and print it with print sales data and sales to see the trend. To find the increase, we use increases equals np.diff sales, which computes differences between consecutive values, and print it with print increases, expecting 5, 5, 5, 5. We calculate the average increase with avg increase equals np.mean increases, and print it with print average increase, avg increase, which should be 5. The prediction comes with next value equals sales minus 1 plus avg increase, adding the last value to the average, and print predicted next value should give 125. To add realism, we introduce noise with noise equals np.random.normal 0, 2, 5, a 5-element array of random noise, and combine it with noisy sales equals sales. We recalculate increases with noisy increases equals np.diff noisy sales. The average with noisy average increase equals np.mean noisy increases, and the prediction with noisy next value equals noisy sales minus 1 plus noisy average increase, printing it with print predicted next value with noise and noisy next value. Let's run this, analyze each step, and explore how NumPy handles noisy data for real-world predictions. As we wrap up this practical exploration, we've applied NumPy to analyze datasets with statistical tools, generated random numbers for simulations, and built a mini trend predictor project. We imported the library, created and analyzed arrays, computed stats, generated random data with control, and predicted trends with noise, all while using Jupyter for interactive learning. These applications show how NumPy powers machine learning prep, from data cleaning to model prototyping. How do you see yourself using these skills in your next project? Looking forward? Imagine analyzing a real data set like stock prices or weather patterns with these techniques. Why not try generating a larger random data set or enhancing our predictor with a moving average in Jupyter? Download a public dataset, say from Kaggle, and experiment with NumPy's functions to uncover trends. Each practice session builds your confidence, and we'll take these skills further in our next episode with new challenges. That's all for Part 3, Code Pilots. You've mastered practical NumPy applications with detailed examples and projects. If you loved this, hit that like button, subscribe for more, and share your thoughts or project ideas in the comments. The adventure continues. Stay tuned, keep coding, and I'll see you next time. Hey there, Code Pilot. Welcome to Part 4 of the Python Machine Learning course, where we're mastering pandas for data manipulation. In the last 3 episodes, we conquered NumPy. Now, we're stepping up to handle structured data with pandas, the go-to library for data analysis. We'll load datasets, clean and transform data, and perform advanced operations to prepare for machine learning. Whether you're new or continuing, this is your launchpad to data mastery. Open your Jupyter notebook, and let's dive into these practical examples with detailed line-by-line guidance. Let's explore what mastering pandas means. Pandas lets us work with tabular data, like spreadsheets or SQL tables, using data frames and series. We'll learn to load data from files, clean messy datasets by handling missing values, and transform data with operations like grouping or merging. These skills are crucial for pre-processing data before feeding it into ML models. To start, let's set up our Jupyter environment, import pandas, and walk through loading a sample dataset step by step. Imagine working with sales data, and let's make it happen with detailed explanations. Why is pandas mastery so vital? In machine learning, clean and structured data is the backbone of successful models. Pandas helps us load CSV files, handle missing entries, and reshape data for analysis. It's used everywhere, from financial modeling to social media analytics. A solid grasp of data manipulation saves time and boosts accuracy. Today, we'll load a dataset, clean it, and perform advanced operations, exploring each line of code with examples and discussing how these skills apply to real-world ML projects. Let's begin by loading and exploring a dataset. We start with import pandas as PD, which imports pandas and lets us use PD as a shorthand, our key to data manipulation. Next, we load a sample CSV with df equals pd.readcsv sampledata.csv, assuming we have a file with sales data, turning it into a data frame. We print it with print dataframe nen df to see the structure. To check the shape, we use print shape df.shape to get rows and columns. We inspect the first few rows with print first 5 rows nen df.head and get basic stats with print summary stats nen df.describe. Let's run this, look at each output, and discuss what these reveal about our data. For missing values, we check with print missing values nen df.isna.sum to count nulls per column, setting the stage for cleaning. Now, let's clean the dataset. We start by filling missing values with df equals df.fillNA 0, replacing nulls with 0, and print the updated data frame with print after filling na.df to confirm. To drop rows with any missing data, we use df equals df.dropNA, printing it with print after dropping na.df to see the result. We remove duplicates with df equals df.dropDuplicates, printing it with print after dropping duplicates na.df. To rename a column, say sales, to revenue, we use df equals df.rename columns equals sales revenue, printing it with print after renaming na.df. Let's execute each step, review the changes, and discuss how cleaning improves data quality for ML. Let's perform advanced data operations. We group data by a column, say region, with grouped equals df.groupB region, and calculate the mean with print mean by region grouped.mean. We merge two data frames, df2 equals pd.dataframe north and target and 100, using df equals pd.merge df2 on equals region, printing it with print after merge df. We use df equals df.sort values revenue ascending equals false, printing it with print sorted by rev. As we wrap up this pandas journey, we've loaded datasets, cleaned messy data, and performed advanced manipulations. We imported the library, read and explored data, handled missing values and duplicates, and applied grouping and merging, all in Jupyter for hands-on learning. These techniques are the foundation for effective ML data prep. How confident do you feel applying pandas to your next project? Looking ahead, imagine analyzing a real dataset like stock prices or customer reviews with these skills. Why not load a Kaggle dataset and try cleaning it with pandas? Or experiment with a custom merge? Each practice session sharpens your abilities, and we'll build on this in the next episode with more ML tools. That's all for Part 4 Code Pilots. You've mastered pandas for data manipulation with detailed examples. If you enjoyed this, hit that like button, subscribe for more, and share your ideas in the comments. The adventure continues. Stay tuned, keep coding, and I'll see you next time. Hey there, Code Pilots. Welcome to Part 5 of the Python Machine Learning course, where we're stepping into the exciting world of data visualization with Matplotlib. After mastering NumPy for numerical foundations and pandas for data manipulation, now it's time to transform our data into visual stories with charts and graphs. Whether you're new to the series or joining from the last episodes, this is where we bring insights to life. Open your Jupyter notebook and let's dive into this visual adventure with hands-on examples. Let's explore why visualization is such a vital skill. Matplotlib acts like a canvas for data scientists, allowing us to create graphs that uncover trends, highlight outliers, or show patterns that raw numbers might hide. Imagine plotting daily sales to see growth over a week, or using bars to compare sales across regions. These visuals make data actionable. We'll start with the basics like line and bar charts, then add customizations like colors and labels, building everything step by step as we code. So let's get our setup ready and jump right in. Visualization is more than just eye-catching graphics. It's a cornerstone of machine learning workflows. It helps us explore data before building models, debug unexpected results, and share findings with teams or clients. For example, A line chart can reveal how sales climb over time, while a bar chart might show which region performs best. Matplotlib offers the flexibility to create these visuals with precision, making it essential for everything from simple analysis to complex ML presentations. Today, we'll craft these plots, customize them thoroughly, and interpret the results. Let's move to the code and break down every step with real-world context. Let's create our first visualization, a line plot. We begin by importing Matplotlib with import matplotlib.pyplot as PLT, which loads the plotting library and gives us the PLT shortcut for all our drawing tasks. This is the backbone of our visual work. Next, we need some data to work with. So we define x equals 1, 2, 3, 4, 5, a list representing days in a week, and y equals 10, 20, 25, 30, 35, a list of corresponding sales figures. Think of this as a simple sales log. We plot this data with plt.plotxy, which draws a line connecting these points to show the sales trend over time, like a steady increase day by day. To display this graph, we use plt.show, which renders it in Jupyter. Let's run this and observe the basic line that appears, then discuss how it helps us visualize a rising trend at a glance. To make it more informative, we add a title with plt.title sales trend, placing sales trend at the top to give context to the chart. We label the x-axis with plt.xlabel days to indicate the time scale, and the y-axis with plt.label sales to show what the numbers represent. Running plt.show again displays this labeled version. Let's analyze how these labels transform the plot into a clear narrative about sales growth, and consider how this could be used in a business meeting to explain performance. Now let's switch gears and create a bar chart to present data in a new way. We reuse our x and y data, but this time use plt.bar xy to generate vertical bars instead of a line. Each bar stands for a day's sales, making it easy to compare individual values side by side. We run plt.show to see the result, and let's take a moment to notice how the bars offer a different perspective compared to the line, emphasizing daily sales distinctly. To add some visual flair, we customize the color with plt.bar xy, color equals blue, where blue makes the bars pop on the screen, and plt.show displays it. Let's point out how color can draw attention to key data points. We can refine the appearance further by adjusting the bar width with plt.bar xy color equals blue, width equals 0.5, where 0.5 reduces the width for a neater layout, and after plt.show, we'll explore how this width adjustment affects spacing and readability. To polish it off, we add labels. plt.title, sales by day, sets a descriptive title. plt.xlabel, days, marks the x-axis. And plt.ylabel, sales, labels the y-axis. Then plt.show reveals the final chart. Let's break down how this bar chart helps us compare daily sales effectively, and think about using it to showcase regional sales differences in a real-world report. Let's elevate our skills with an advanced plot that compares two datasets. We introduce a second sales metric with y2 equals 15, 22, 28, 32, 40, imagining this as an updated sales forecast or a different product line. We plot the original data with plt.plotxy label equals original, where original tags the first line for identification, and add the new data with plt.plot xy2 label equals new. Tagging the second line. Both share the same x-axis for days. To display these labels, we add plt.legend, which creates a small box identifying each line, and plt.show renders it. Let's run this and see how the two lines let us compare the data sets side by side. To improve readability, we add a grid with plt.grid true, which draws horizontal and vertical lines as reference points, and plt.show updates the view. Let's note how the grid makes it easier to trace values. We enhance the plot further with plt.title sales comparison for context, plt.xlabel days for the x-axis, and plt.ylabel sales for the y-axis. Then plt.show displays the complete version. Let's dive into how this multi-line plot with a grid helps us spot differences like forecasting accuracy, and discuss how this could be used to present machine learning model comparisons to stakeholders or clients. As we conclude this detailed exploration of visualization, we've learned to create line and bar charts, customize them with titles, labels, colors, and grids, and compare multiple data sets with advanced features. We started by importing Matplotlib, built our first plots, refined them step by step, and added comparisons, all within the interactive Jupyter environment. These skills open the door to exploring data visually and communicating insights effectively in machine learning projects. How do you envision using these visualization techniques to enhance your next data analysis? Looking ahead, why not challenge yourself by visualizing a real-world dataset, like temperature trends or website traffic from Kaggle using Matplotlib? You could try scatter plots to explore correlations, experiment with different colors or line styles, or even add annotations for key points. Each practice session sharpens your visualization skills, and we'll build on this in future episodes with more advanced ML tools and techniques. That's all for Part 5, Code Pilots. You've mastered the art of data visualization with Matplotlib through thorough, hands-on examples. If you enjoyed this deep dive, please hit that like button, subscribe for more episodes, and share your feedback or visualization ideas in the comments. The journey continues. Keep coding, stay curious, and I'll see you in the next one. Hey there, Code Pilots! Welcome to Part 6 of the Python Machine Learning course, where we're embarking on an exciting journey into machine learning with Scikit-learn. After mastering NumPy, Pandas, and Matplotlib, now it's time to build predictive models and unlock the power of AI. Whether you're new to the series or continuing, this episode will introduce you to the fundamentals of machine learning. Open your Jupyter notebook, and let's dive into this new chapter with practical examples. Let's begin by understanding what machine learning is all about. It's the process of teaching computers to learn from data and make predictions or decisions. Think of predicting house prices or classifying emails as spam. Scikit-learn is our go-to library, offering tools to train models like regression or classification. We'll set up our environment and prepare a simple dataset. Then build our first model step by step. Imagine using past sales data to forecast next month's numbers, and we'll get there together. Machine learning is the heart of modern data science, powering everything from recommendation systems to self-driving cars. It involves training a model on data, testing it, and refining it. Scikit-learn simplifies this with pre-built algorithms. Today, we'll cover the basics: what supervised learning means, how to split data into training and testing sets, and how to evaluate a model. Let's move to the code and explore each concept with detailed, hands-on examples to see how it applies to real ML projects. Let's build our first machine learning model. We start by importing Scikit-learn with from scikit-learn.linear-model import linear regression, which brings in a simple regression model to predict numerical values. This is our first ML tool. We also import train test split from scikit-learn.model selection for splitting data. Next, we create a sample dataset with x equals 1, 2, 3, 4, 5 as our input features, like days, and y equals 10, 20, 25, 30, 35 as the target, like sales. We split this into training and testing sets with xtrain, xtest, ytrain, ytest equals train test split x, y, test size equals 0.2, where test size equals 0.2 reserves 20% for testing. Let's run this and discuss how splitting prevents overfitting. We create the model with model equals linear regression and train it with models.fit xtrain ytrain, which learns the relationship. Let's explore what this training step does. Now let's make predictions and evaluate our model. We predict on the test set with ypred equals model.predict xtest, which generates predicted values based on the trained model. We print predicted values, ypred, to see the results, and let's compare them to ytest to get a sense of accuracy. To measure performance, we import mean squared error from sklearn metrics and calculate error equals mean squared error, ytest, ypred, printing mean squared error, Holman's error. Let's run this and talk about how this error metric shows how far off our predictions are. We can visualize the fit with a simple plot later, but for now, let's focus on understanding these numbers and what a good error looks like. Let's refine our model with more data. We expand x to 1, 2, 3, 4, 5, 6, 7, and y to 10, 20, 25, 30, 35, 40, 45, adding 2 more points. We split again with xtrain, xtest, ytrain, ytest equals train test split, xy, test size equals 0.2. Train with model.fit, xtrain, ytrain, and predict with ypred equals model.predict, xtest. We calculate the new error with error equals mean squared error, ytest, ypred, and print both new predicted values, ypred, and new mean squared error, error. Let's run it and analyze how more data improves or changes the fit. We'll discuss how this iterative process is key to tuning ML models for better performance. As we wrap up this introduction to machine learning, we've learned the basics of Scikit-learn, built a linear regression model, split data, trained it, made predictions, and evaluated performance. We imported the library, prepared a dataset, used train test split, fitted the model, and calculated errors, all in Jupyter. These foundational skills are your entry into predictive modeling. How do you see yourself applying this to predict real-world outcomes? Looking ahead, try applying this to a real dataset, like the Iris dataset from Scikit-learn, with different models or features. Experiment with adjusting test sizes or exploring classification tasks. Each practice builds your ML expertise, and we'll dive deeper into advanced techniques in the next episode. That's all for Part 6, Code Pilots. You've taken your first steps into machine learning with Scikit-learn through detailed examples. If you enjoyed this, hit that like button, subscribe for more, and share your thoughts or project ideas in the comments. Keep learning, keep coding, and I'll see you next time. Hey there, Code Pilots. Welcome to Part 7 of the Python Machine Learning course, where we're taking our Scikit-learn skills to the next level with advanced machine learning techniques. After introducing regression in the last episode, now it's time to explore classification, evaluate models deeply, and improve performance. Whether you're new or continuing, this episode will build on your foundation with practical examples. Open your Jupyter notebook and let us dive in. Let us start by understanding what is next in machine learning. Classification predicts categories, like identifying if an email is spam or not, unlike regression's numerical predictions. We will use the iris dataset to classify species, evaluate with multiple metrics, and tweak our models for better results. We will set up our environment, load the data, and work through each step. Imagine building a model to sort flowers, and we're going to do it together. Advanced machine learning is about refining models for real-world accuracy. Classification adds a new dimension, requiring metrics like accuracy and precision, while techniques like cross-validation ensure robustness. Scikit-learn's tools let us experiment and optimize, crucial for tasks like fraud detection or medical diagnosis. Today, we will cover classification, evaluation with multiple metrics, and performance tuning. Let us move to the code and explore each concept with detailed examples. Let us build a classification model. We start by importing Scikit-learn with from scalarn.linear model, import logistic regression, and train test split from scalarn.model selection. We load the iris dataset with from scalarn.datasets, import load iris, then iris equals load iris to get the data. Let us print iris.data 5 and iris.target 5 to see features and labels. We split with xtrain, xtest, ytrain, ytest equals train test split, iris.data, iris.target, test size equals 0.2. Run this and discuss how this prepares data for classification. We create the model with model equals logistic regression and train it with model.fit xtrain, ytrain. Let us explore how this learns to classify species. Now let us make predictions and evaluate with multiple metrics. We predict with ypred equals model.predict xtest and print predicted labels, ypred. Let us compare to ytest to see accuracy. We import accuracy score and confusion matrix from sklearn.metrics. Then calculate accuracy equals accuracy score, ytest, ypred, and print accuracy, accuracy. Run this and discuss what 80% accuracy means. We create a confusion matrix with cm equals confusion matrix, ytest, ypred, and print confusion matrix, cm. Let us analyze how it shows true versus false predictions per class, a key insight for model improvement. Let us improve our model with cross-validation. We import cross-val score from sklearn.model selection and use scores equals cross-val score, logistic regression, iris.data, iris.target, CV equals 5, to get 5-fold validation scores. Print cross-validation scores, and let us calculate the mean with print average CV scores.mean to see overall performance. We adjust the model with model equals logistic regression max iter equals 200. To handle convergence, retrain with model.fit, xtrain, ytrain, and repredict. Let us run ypred equals model.predict xtest and check new accuracy to discuss how iteration improves results. We will explore how this tuning applies to real datasets. As we wrap up this advanced dive into Scikit-learn, we have learned classification with logistic regression, evaluated with accuracy and confusion matrices, and improved with cross-validation. We imported libraries, loaded the iris dataset, trained a classifier, assessed performance, and tuned the model, all in Jupyter. These skills are your next step in mastering machine learning. How do you plan to apply this to classify your own data? Looking ahead, try classifying the Titanic dataset with Scikit-learn, experimenting with different models like decision trees or tuning hyperparameters. Explore precision recall curves or use larger datasets to challenge your skills. Each practice deepens your ML expertise, and we will build on this in future episodes. That is all for Part 7. Code Pilots, you have advanced your Scikit-learn skills with detailed, practical examples. If you enjoyed this, hit that like button, subscribe for more, and share your ML ideas or questions in the comments. Keep coding, keep learning, and I will see you next time.